Welcome to session 3. So that does mean now that you're halfway done, very close to that. We begin session 3 with roots. Now these are not going to be roots as in solutions, but rather roots as in radicals. So 3A we'll call roots. Nice short section. We have square root, and everyone in the world knows that the square root of 4 is 2. Notice that pause there. I said everyone in the world knows the square root of 4 is 2. My night job, I teach at a university level. So one of my favorite things to do there is to investigate the square root of 4 or something like that. So every class I teach there, somewhere you wind up taking a square root. And so, I'll say square root of 4 is 2. Everybody agree? And, some will even say yes, but everybody will be shaking their heads. And I'll say, well, are you sure it's not plus or minus 2? Then I'll say, well, is the square root 4 2? Or is it plus or minus 2? And, a lot of students will then say, yep, it's plus or minus 2. That's right, the square root of 4 is plus or minus 2. And then I'll say, what is it, 2 now? Or is it plus or minus 2? And then there's all this confusion. But, a few minutes ago, everybody in the world was pretty sure that the square root of 4 is 2. So let's go to the paper here and talk about where this confusion comes from, because there is a whole bunch of confusion about this. It is the case that 4 has 2 square roots. One of them is 2 and one of them is negative 2. However, it is your responsibility to write down, if you wish to indicate that 4 has 2 square roots, you have to write plus or minus 4 is plus or minus square root of 4 is plus or minus 2. So if you want to indicate that there are 2 answers, you've got to put that plus or minus there. Here's where the confusion comes from, I believe. If we're now doing a little aside, but if I were solving the equation x squared is 4, one way I would solve that equation is by taking the square root of both sides. Square root of x squared is square root of 4. Now the square root of 4, my assertion is that the square root of 4 is only 2. The square root of 4, when it's written down like that, is only 2. It's not plus or minus 2. But here's what really happens. What is the square root of x squared? Well, the square root of x squared isn't x. Yeah, square root of x squared is absolute value of x, but you see nobody bothers writing that step down, and that's where all the confusion comes from. So if you solve the equation that the absolute value of x is 2, from that you get x is plus or minus 2, but unfortunately we've been conditioned to go from here right down to there, and then that's why everybody's confused about what the correct answer is up here. The agreement is when you write down square root of 4, the agreement is that that's positive 2, so you're talking there about the principal square root. That, of course, keeps the square root function as a function instead of being a relation, and we would like the square root function to be a function. Okay? So now we've thoroughly agreed that the square root of 4 is 2, and that actually makes good sense. Now, cube root 27, so it's going to be a 3. Fourth root 16. Nobody in this room is going to say plus or minus 2. And actually 16 has 4 fourth roots, but 2 of them are complex. Okay. But what we want is the primary one, which is 2. Fifth root negative 32. Now, in the set of real numbers, you can't take even roots of negative numbers, but you can take odd roots. And if you take the odd root of a negative number, then your answer is a negative. And since 2 to the 5th is 32, the 5th root of negative 32 is negative 2. Let's see how the calculator might have done those problems. come to the calculator over here. Okay, so I've got it turned on. If I want to find the square root of 4, here above the x squared, there's a square root. So I can go yellow button square root, and then put a 4 in there. Now the TI-83 prompts the first parenthesis. I didn't have to push a button to get that. And it's again my thought that the TI-83 always forgives you if you forget to put the very last parenthesis, but my colleagues tell me I'll be a better math teacher if I go ahead and put that last parenthesis. And they say, Dave, you might as well do it right. So square root of 4, well, look at there, even the TI-83 agrees that it's only 2 and didn't say 2 and negative 2, so that's pretty good. Now to find a cube root, there actually is a cube root. If you look in math, I'm going to go math. Number 4 is a cube root. I'll push a 4 and find a cube root of 27. Put the parenthesis in there, Dave. And that does tell us 3 was the answer. Now to find 4th roots and higher there is that button there that had the xth root, but you can do the fraction exponent too. So if I wanted to find the 4th root of 16, what I would do is put 16 upper 1/4, and I can even put that as a decimal if I want to, and the calculator knows how to find all that stuff. Okay, so let's try to find the 5th root of negative 32. Now I do have to put that negative there. Well, actually the answer would be the same, but to be correct I would have to put that. And I want the 5th root, so that's 2/10. Do that, negative 2, or I could have done negative 32 upper 1/5, 1 divided by 5. That works perfectly fine. Okay, so that's about what there is to roots. We're going to, of course, extend roots in the next section when we talk about rational exponents. So this was a very short section. It doesn't hurt to have short sections every now and then. We're probably going to find another long section somewhere in this section to make up for it. You can do 3A and enjoy doing so. Session 3, Part B, Rational Exponents. Okay, by x to the p over q power, we mean do this. You can take the qth root of x to the p, or if you prefer, you can do the qth root of x and raise that to the p. That, of course, is certainly good if x is a positive number. So if I wanted to compute 8 to the 2/3 power, I have my choice, you see. My choices are, I can find the cube root of 8 squared, or I can find the cube root of 8 and square what we get. Since you get the same answer either way, my choice would be the second one. Now the reason that I would choose the second one is you get to mess with smaller numbers. So it's easy to find the cube root of 8, that's 2. 8 squared is 64. It's not bad to find the cube root of 64, but it's certainly a lot nicer to find the cube root of 8. And so I would say this is 2 to the 2nd power, and that gives 4. Of course, this is also 4 because the cube root of 64 is 4. Let's practice a few more of those. Okay, so I'd like to find 4 to the negative 1/2 power. Now that negative exponent means what it's always meant, and that's to do a reciprocal. The 1/2 power says take the square root of 4, and as we all thoroughly know, the square root of 4 is 2, and so 4 to the negative 1/2 power means do that. Okay, I'd like to evaluate 16 to the 7/4 power. 16 to the 7/4 power. Well, that would mean take the 4th root of 16 and whatever you get raised to the 7th power. Or, it could mean take 16 to the 7th power and then find the 4th root of that. Right, I'd really do it that way. So here we've got 2 to the 7th. Now to find 2 to the 7th, I guess in today's world you go over to your calculator here and you push the 2, and you push the upper caret 7, push the enter, and you get 128. So the calculator probably wouldn't have mind. Let's go over and see what that calculator would do. I could do 16 to the 7th power, is that number, and then find the 4th root, so raised to the 0.25, and it still turned out to be exactly 128. I thought it might have turned out to have been like 127 to the 0.999992 or something like that, but this one did turn out exact. Keep in mind that the technology, although very good, is not perfect. Just isn't perfect. Okay, well, let's do a little bit more radical stuff in fraction exponents. Here I've got, well, I'll simplify these expressions. I want to take the 4th root of 8 and multiply it by the 4th root of 2. 4th root of 8 times the 4th root of 2. Now on the one hand, I guess I could use my calculator and figure out what the 4th root of 8 is and figure out what the 4th root of 2 is, and then, go ahead and multiply those two together. But on the other hand, I could do 4th root of 8 times 2, which is 16, and then that way the answer does turn out to be 2. Let's go to the calculator and try it the silly way. Okay, so I'm going to do the 4th root of 8, 8 to the 0.25 power. All right, now I'm going to take that and multiply it by, the calculator has this very nice feature that if you do chain operations, by that I mean, see, I just did an operation, and I've got 1.68, whatever it is there displayed. Now if I push an operation button, say like times, notice it says answer times. So automatically the last number that comes up on the right here is stored in that place called answer. If we can come over to the calculator here. Okay, automatically the last thing on the right side is stored in this place called answer, and if you'd like to access that, above your opposite sign is answer. But here, all I did is push the times. Let me go through that again. I pushed 8 upper 0.25 and pushed the answer there. All I did is push the times button. See, I'm going to come over here and I'm going to push times. It says answer times, and now I'm going to push 2 upper 0.25, and it turned out to be exactly 2 again. Well, now you do know that the 4th root of 8 and the 4th root of 2 are irrational numbers, so we were lucky in that the way that these rounded off here, the rounded off final answer did again turn out to be a 2. So that's why I thought it might turn out to be a 2.00001 or something like that. Technology Very good. Not perfect. Okay. Well, that all looks pretty good. We'll try just one more. You go ahead and find square root of 50. Now that seems like a remarkably simple one for just one more. I guess I can come over to the calculator here and find square root of 50. So I'll go yellow button and 50, and the calculator tells me the answer to that is 7.071. Now, in our algebra courses, we teach students that the square root of 50 can be written as 5 square roots of 2, because 50 is 25 times 2, so we can take out that 25 and make it a 5. Let me go ahead and calculate that again. So here I come to 5, then I push the square root of 2, enter, and of course we get the same answer. That's somewhat comforting. Now let's see. Which is the simplified version? Square root of 50 or 5 square roots of 2? You see, in today's world, we might have to change our notion of which the simplified version is, because I think it was easier, as a decimal to compute just the square root of 50 instead of going through the thinking process of changing this and then computing it. I think it was much quicker to have left it in the unsimplified version. So it could be that we're heading for a world in which the problem says 5 square roots of 2 and the direction says simplify, and you say the answer is the square root of 50. We're not probably there yet. But now, that doesn't mean that we shouldn't teach students that square root of 50 is 5 square roots of 2, because that's useful for other purposes when you're simplifying radicals with variables and all that stuff. And so that ends session. Oh goodness, this one. Well, that ends session 3B, but I guess I have to tell you the story behind this now. You see, after my lovely daughter gave me that 55 Thunderbird, I started working on my wife seriously. I said, we really need to get some kind of a sports car. Wouldn't it be just so cool to have a sports car convertible that we could go cruise around in? And so, yeah, that's what she did. She saw all the fun that my daughter had with that 55 Thunderbird, and after I'd worked on her for a while, she gave me this sports car. This is a little ostentatious, I think. It's a Sweet 16 is called their sports car. I don't know if a real car like that ever existed. At least the 55 Thunderbird. There really used to be a car that actually looked like that. Okay. This is I don't think I'd want to drive one of those. But anyhow, my wife had her good fun of giving me my sports car convertible. Yes, that's right. That's the wife that's no longer in the will, too. So wife and daughter, they're not there anymore. Of course, my son and the cat, they're both happy because they're the only two left in that will. That finishes section 2B. You can work those problems. Section 3C. Inverse functions. Inverse functions. First, let me tell you about a thing called composition. And it's called circle operation, if we had this function f of x is 3x plus 5, and this function g of x was x squared minus 1. If I wrote f circle g of x, this is now the fifth operation that you can do with two functions. With two numbers, there's four things you can do to two numbers. You can add them, subtract them, multiply them, or divide them. With functions, you can add, subtract, multiply, and divide, but you can also compose the two functions. So there's 5 operations on two functions, and f circle g of x, what that means is to find f of g of x. Now there's two schools of thought on finding f of g of x, and this symbol, by the way, here does not mean f times g of x. It sure looks like it should, but it doesn't mean that. It means take g of x and put it into function f. There's two schools of thought, one of which is to go from the outside to the inside, and the other of which, of course, is to go from the inside to the outside. You are allowed to decide for yourself which school you belong to. I belong to the school that says go from the inside to the outside. And so this is f of x squared minus 1. So what I did is I took the g of x and replaced it with x squared minus 1. Now, if you're going to have a little bit of trouble with this, look at this function f of x and think of it as f of box equals 3 times box plus 5. That is, think of that x as being a box into which you put something. Now whatever's in the parentheses here, that's what you put in the box. So f of x squared minus 1 becomes 3 times x squared minus 1 plus 5. So I took the x squared minus 1, put it into that box, and then we simplify, getting 3x squared minus 3 plus 5 is plus 2. So there's f circle g of x. And let's go ahead and compute g circle f of x. Now this would mean g of f of x, so I again am going to work from the inside out. F of x was 3x plus 5. So now I have to think of this g of x as being g of box is box squared minus 1. And into that box I want to put 3x plus 5. So it's box squared and then subtract 1. Now there is g circle f. It seems natural to go ahead and carry this out in other steps. 3x squared is a 9x squared. Now you take twice the product, so 15 doubled is 30. It's 30x. It's plus 25 minus 1. That leaves a plus 24. And so we notice that in general, f circle g is different from g circle f. In general, composition is not a commutative operation. You know, there are certain pairs of functions which do commute, but in general, it's not commutative. Now to inverses. Inverse functions. Inverse is a word that students quickly learn to abuse. At least in my school system, students quickly learn to abuse the word inverse. I'll ask my pre-calculus students, what's the inverse of 2? You know what they say, don't you? They say the inverse of 2 is a half, which is correct, but it's not complete. If they told me the multiplicative inverse of 2 is a half, I would be delighted. But somewhere along the line, at least in my school system, we teachers start dropping the completeness of saying the multiplicative inverse of 2 is a half, and we start saying the inverse of 2 is a half. See, why couldn't the inverse of 2 be negative 2? For indeed, the additive inverse of 2 is negative 2. So if I just say what's the inverse of 2, how does everyone decide that I was talking about the multiplicative rather than the additive inverse? I don't know how they make that decision. So pretty early on in the advanced courses that I teach, we make this decision that we're not going to use the word inverse. We're going to use the word reciprocal. So then if I say, what's the reciprocal of 2? Everybody says, it's a half. And I say, yes. All right, so we got that point across there. So my agreement is that when I use the word inverse, it will always be as a functional inverse. So then that just ends any possible confusion. So let's go to the paper, inverse functions. I want to consider this function, f of x equals 2x plus 1, or of course I could write that as y equals 2x plus 1. And then I'd like to find some values. I'm going to do this. If x is 3, y is what? So let's contemplate this. If x is 3, what on earth is y? Well, if you put a 3 in there, you get 2 times 3 is 1. 2 times 3 is 6, plus 1 gives 7. So there again, lots of us are thinking, I hope Carmen puts a lot of those on that quiz, because that was a pretty nice problem right there. I would expect that you're not going to get anything like that on that quiz. If x is 3, y is 7. So let's see if we can do this backwards. If I tell you that y is 9, you tell me what x is. Notice I said we're going to do this backwards. X is 3, y is 7. Now if y is 9, so now I guess what we have to do is start guessing. What number can you put into 2x plus 1 to wind up with a 9? Well, we suspect it's going to be a little bigger than 3. Let's try a 4. 2 times 4 is 8, plus 1 is 9. Aha! So if y is 9, then x is going to be 4. There, we did that backwards, at least in my jargon. When I give you x and you give me y, that's like doing a function forward. If I give you y and you got to give me x, that's kind of like doing it backwards. Let's try one more of those. Y is 5,281. Tell me what x is. I didn't hear anybody say anything here. Oh, that's right. I shouldn't be. Okay, y is 5,281. Let's see if we can guess what x is. Oh, there's somebody. You said 2,640? Well, I guess I'll take your word for that, if I can write it down right. Let's check and see if that was right. 2 times 2,640, add 1, is 5,281. So, yeah, there it is. Okay. Now, what on earth are we doing here? I mean, get with it, Dave. There's got to be something going on here. If you graph the line, y equals 2x plus 1. The line y equals 2x plus 1. First, I said I was going to do this function forward. That is, I gave you 3. And having given you x is 3, you told me that y should then be the number 7. Okay. So then I said, well, let's see if we can do this backwards. I told you that y was going to be 9. What would x be? And you figured out that x would have been 4 if y was 9. And then I decided to be somewhat snotty, and I said, you know, y is 5,281. What on earth would x be? Of course, you all figured out the real way to do that wasn't to guess. The real way to have done that was this way. We had the equation here, y equals 2x plus 1. If I told you that y was 5,281, you just set that equal to 2x plus 1, solve the equation. Subtract 1, 5280 is 2x, and then divide by 2, and get 2640 is x there, right? So I guess that's the real way that we made a good guess. Okay. Well, what on earth are we doing here? Let's figure out first what an inverse is. I guess this will be a definition. G of x is the inverse of f of x. Now you notice I didn't say inverse function, but I didn't say multiplicative inverse, and I didn't say additive inverse, and the agreement in the classes that I teach anyhow, the agreement is that when I use the word inverse, it is a functional inverse. Otherwise I say opposite or reciprocal. G of x is the inverse of f of x if and only if g of f of x is x and f of g of x is x. Here's what this says. If you pick an element, number in this case, and put it through both functions, you get back to where you started, no matter which way you do it. So the notion of an inverse is, you know, if instead of doing functions we were doing some kind of an action, and if I said start is right here, and my action is to take 2 jumps to the right, if that was the action, then the inverse of that action would be take 2 jumps to the left. So if I take the 2 jumps to the right and then take the 2 jumps to the left, I get back exactly where I started. Of course, if I start here and take 2 jumps to the left and then do its inverse, 2 jumps to the right, I get back to where I started again anyhow. That's the notion of an inverse, of getting back to where we started. Let's check this. On the one hand, I had f of x was 2x plus 1, and what did the inverse there turn out to be? What did we actually do here? To get this x by itself, that is to get back to where I started, I subtracted 1 and divided by 2. Subtracted 1 and divided by 2. Yeah? Put a 5281 there, subtracted 1, divided by 2. So it should be, I say it should be, that if I compose these two together in either direction, I wind up with just x. Let's try it. Let's try f of g of x. It's f of x minus 1 over 2. And so f of x doubles and then adds 1. So we double, add 1. Well, simplifying this, 2's cancel out. I get x minus 1 plus 1. That winds up being x. Let's try it the other way. F of g of x becomes f of, that's the one we just did. So let's try g of f of x. I sure hope we would have gotten the same thing that way. Lord. F of x, 2x plus 1. I'm going from the inside out. Now function g subtracts 1 and then divides by 2. So here I take 2x plus 1. I got to subtract 1 and divide by 2. Where some 1's cancel out, and 2x over 2, that does give x. Right? So both ways, the composition resulted in y equals x. Now, if we were to make some generalizations about inverses, the notion of an inverse, for addition, the inverse element is that element that gets you back to 0. The additive inverse of 2 is negative 2. If you add those two together, 2 and negative 2, you get 0, which is the identity element for addition. For multiplication, the multiplicative inverse is the reciprocal, of course, for not 0. So multiplicative inverse of 2 is a half, and if you multiply 2 times a half, then you get 1, which is the multiplicative identity. So what's happening with functions? The inverse of a function is whatever function gets you back to where you started. In other words, whatever you start with, that's what you wind up with, the identity element. So the line y equals x is the identity function. It's all the same concept. Well, here's another way to look at it. This is a function box. So 2x plus 1 function box. This is the crank. Okay, so this is the 2x plus 1 function box. I take the number 3, I put it into the top, turn the crank, and out the bottom comes 7. Okay. So what does the inverse do? Well, in the inverse, what we do is do this backwards. We take the number 9, put it in the bottom of the function box, turn the crank backwards, and out the top pops 4. F of 3 is 7. F inverse of 9 is 4. This is an old-time function box. Most of you are probably a lot younger than me. You've probably seen the modern function boxes where instead of this crank here, they've got a button that you push instead of the crank there. That's the modern function box, but the old-fashioned ones have a crank there. And then, of course, you can take 5,281, put it in the bottom, turn the crank backwards, and out the top pops 2,640. I don't know how you do that do it backwards with the button. I guess you pull the button out instead of pushing it back in. Well, are we always going to be able to do this? Are we always going to be able to put one number in the bottom, turn the crank backwards, and get one number back out the top? See, if that's true, that means we can reverse or find the inverse for functions, and the inverse function itself will be a function. Well, in a few minutes we're going to be wondering that question in more detail. But for now, let's go ahead and find the rule for an inverse. So here's going to be a function. F of x is 3x plus 5. What I'd like to do is I'd like to find f inverse of x. Now the symbol that we use for an inverse is the same symbol that we use for a reciprocal. So that adds to the confusion. I mean, look at the calculator over here. Let's go to the calculator. The buttons on the calculator, this -1 right here, that's a button for a multiplicative inverse or a reciprocal. That is not a button for a inverse function. I don't know how many times I've had a student become really confused, especially with the trig functions. If you look over here now, in this course, we don't get to do the trig functions in this course, but in another course, here's the button, the sine button, and above it is sin to the negative 1 power. That's an arc sine. That's the inverse, the function inverse of the sine function. But I don't know how many times I've had a student who thought he or she could find an arc sine by pushing sine and then pushing that negative 1 button, and of course that's not what it is. If you push sine and the x to the negative 1 power, that gives you a cosecant, the reciprocal of the sine. But I've had a lot of students very confused about that. So it seems as though this is maybe a bad symbol. If we can come over to the paper here now. I think if I were the king of the whole world, I would have created some different symbol. Instead of saying f to the negative 1 power for an inverse, I'd have called it f star or something like that, some different symbol for an inverse. Turns out in the old days when the symbols were being made up, they didn't have computers with quite as many fonts and stuff as we have today. They did typesetting. So back in the old days, there were only a small number of symbols that were available, and so they had to, start using the same symbol with different meanings. But that does cause a lot of confusion. None of us will ever be confused about that, because we all know that when you see a negative 1 on a function, it means a function inverse, and when you see a negative 1 exponent on a variable, it means a reciprocal. Okay, I want to find the inverse, and this is what you do. First, you replace y with f of x. Now, the only reason that you replace the f of x with a y is that it's easier to manipulate that way. Okay. Now, what I'm going to do is just solve this equation for x, just like we did when I said y was 5,281. We went ahead and solved that equation for x. So I'm going to subtract 5. Y minus 5 is 3x, and then we divide by 3, and so I get y minus 5 over 3 is x. So what this is telling us to do, for a given y coordinate, if I would like to find the x coordinate that corresponds, that is, I give you 9, you give me 4, if I'd like to do that, for this function, what I have to do is subtract 5 and divide by 3. So the way it should be is that we write, if g was the inverse, we should write g of y is y minus 5 divided by 3. See, that actually makes good sense, because if I'm going back now to that 2x plus 1 thing, I told you x was 3, you told me that y was 7, I told you that y was 9, you tell me x, and you told me x was 4. So what kind of a number do you put into the inverse? It's actually a y value that you put into the inverse, not an x value. So it should be that g of y is y minus 5 over 3. However, it isn't going to be. We do this thing of switch the coordinates. So instead of writing this, we'll write x minus 5 over 3 is equal to y. And up here it says f inverse of x, and we write x minus 5 over 3. Now, why do we switch the x and the y? See, I don't know. I don't know why we switch the x and the y. I've been asking students for a long time now why you switch the x and the y. When I get them into pre-calculus, in their previous course they learned how to find the inverse function, and I usually ask somebody to help me out and find this, and they'll tell me, oh, switch the x and the y. And I'll say, why do you switch the x and the y? And then they give me this blank look, and they'll say, Miss Bailey told us to do it. So that's why, last year Miss Bailey said switch the x and the y. So, okay, well, that's a good enough reason right there. But it seems to me as though there's no logic behind switching that x and the y. And it seems to me that there would be less confusion if we left it g of y, but the rest of the world is putting an x in there. And so, there are times that it's smarter to not fight, just do what they say to do. I believe the only reason that you switch the x and the y here is that students are more comfortable having the x being the input and the y being the output. But somewhere somebody got the idea to switch the x and the y, and it's kind of nice that they did that. But I think there's no logic behind that. Well, let's see if this in fact is the correct inverse. So the claim is that if f of x is 3x plus 5, then f inverse of x turns out to be x minus 5 over 3. Let's go ahead and compose those together. So f of f inverse of x would then become f of x minus 5 over 3. Now f triples and then adds 5, x minus 5 over 3. And if we simplify that, we see, lo and behold, we do get an x. It works in the other direction as well. And so we've found the inverse. G of x is x cubed minus 2. I'd like to find G inverse of x. Well, it's the same process. First you put the y in for the g of x. And then we're going to go ahead and switch the x and the y. And then you do whatever it takes to solve the equation for y. So I'm going to add 2 and take the cube root. And so, there it is. Now you can check if you want to. Leave that to your discretion. Well, everything seems to be going fairly well. Yeah. Let's try f of x is x squared. Let's find f inverse of x. Well, we put y equals x squared. Going to switch the x and the y. Alright, so we're going to switch that x and y. Now, we switch the x and the y. I say just because it's what we're supposed to do. So we're behaving nicely. Well, we've talked about this before. What I have to do to get y by itself is take the square root, but when you're solving equations, you actually get that absolute value, so plus or minus square root of x is equal to y. Now we've got trouble. The reason we've got trouble is this inverse itself is not a function. And sometimes that's okay, but sometimes you want your inverse itself to be a function. So we've got trouble. The reason that that happened is, if you look at the graph of x squared, see if I had this x squared function box, I'd do the old-fashioned one with the crank. Let me pick a number 3 for x. Right? So if I take a 3 and put it in there and turn the crank out, the bottom comes a 9. But now you see, if I try to do this backwards, if I had taken the 9 and shoved it in the bottom, turned the crank backwards, out the top could have come 3, but out the top could have come -3 as well. So when we do this one backwards, a given input has 2 outputs, meaning that the inverse itself is not a function. In order to fix that problem, sometimes what we do is restrict the domain of the original function. So if we had y equals x squared for x greater than or equal to 0, then what we would say is that f inverse of x is square root of x, And of course, if we had chosen x less than or equal to 0, we would say f inverse of x is negative square root of x then. This function x squared doesn't have a certain property, and that property is one-to-oneness. If I draw a horizontal line here, I notice that that horizontal line touches the graph 2 times, so that means a given y-coordinate like 9 is associated with 2 different x-coordinates, 3 and negative 3 here. It turns out that if your original function is 1-to-1, then you don't run into this problem here. So here's a thing called the horizontal line test for 1-to-oneness. Horizontal line test. If every horizontal line intersects a graph at most one time, the graph is 1-to-1. Then it will have an inverse. So okay, let's talk about graphs of inverses. Well, let's find one or two more first, and then we'll talk about graphs of inverses. Pretty neat. F of x is 2x plus 5 divided by x minus 3. Find f inverse of x. Well, first I'm going to put y equals 2x plus 5 over x minus 3. And then we have to do whatever it takes to get the x by itself, or switch the x and the y first. It's scholar's choice, right? You can either switch the x and the y first or switch it last, but at some point you got to switch it. So now, got to do whatever it takes to solve that equation for a y. Well, I'm going to multiply both sides by y, and I get a xy minus 3x is 2y plus 5. Now, a lot of my students would go ahead and subtract 5 and divide by 2 and say, there it is, I got the y by itself. We, of course, know that that's not solved for y because you still got some y's over here on this other side. So the thing to do is to gather all the y's on one side, and anything that doesn't have a y, put on the other side. So we got a xy minus a 2y equals 3x plus 5. And the reason we would want to do that is I can factor a y out of there. And then divide by x minus 2. And so there's the inverse. I got a 3x plus 5 divided by x minus 2. Well, I guess if I were a little bit more courageous, I'd go ahead and compose those two and see if it actually works, but we'll let those among you who are courageous go ahead and compose those two functions and see if you actually do get the identity. Darn. I'm going to show you a different way to check. Well, to sort of check. Alright, we switched the x and the y. If Dave Oberly was the king of the world, we wouldn't have switched the x and the y. But something really neat happens when you switch that x and the y. So it's a good thing that I'm not the king of the world. Let's go to this graph paper here and let me show you something. Alright. Now, I'm going to draw here the line y equals x. So that's the line that goes through 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, like that. Missed it by a little bit. Let me try that over again. I want this to be as exact as I can make it. I'm going to try that one again. Okay, try a little bit better this time. Better. Okay. So this is the line y equals x. The identity graph. Now I'm going to pick 3 points that I know are below that line. So I guess I'll pick here, let's see, this would be -1, -2. And let me pick a point, I guess right here. This would be 3, -3. And let me pick a point up here somewhere. Oh, where's a good place to pick one? There. Maybe up here. That looks like a pretty good place. Maybe way up there. How about over here? That looks like a pretty good one right there. 0.41. Okay, so let's suppose that these are points x, y on some graph. Now what I'm going to do is switch the x and the y coordinates. So instead of 4, 1, I'm going to find 1, 4. 1, 2, 3, 4. Okay, there's 1, 4. Instead of -1, -2, I'm going to graph -2, -1. -2, -1. Instead of 3, -3, I'm going to graph -3, 3. Okay, now let me go ahead and draw this triangle. And let me draw this triangle. And what do we notice? My goodness, we notice that this graph seems to be the mirror image of that graph through the identity graph y equals x right here. That's what happens when you switch the x and the y coordinates. Your graph always turns out to be the mirror image through the line y equals x. Now I think there might be some significance to that. I think, relating to graphs, if you knew the graph of a function, you could find the graph of the inverse by reflecting that graph through the line y equals x. Yeah? Pretty cool. Well, next thing we're going to do is to investigate some of that stuff and see how the graph of a function and its inverse are related to each other. I think I'm going to do one more finding the rule for an inverse. The reason for that is I just have this suspicion that Carmen might have it in mind to put something like this on your quiz. Right? I think she might be that tough that she'd do something like that. So the request here is to find the rule for f inverse of x. Now we don't have to check it, right? We just have to find the rule, see how that works. Okay. Incidentally, there's anytime that I ask you, here's a function, find f inverse of x, the function will be a one-to-one function, so you don't have to worry about whether a function is one-to-one. If you were worried about that, you can always graph the function on your TI-83 and use the horizontal line test. But let's go ahead and do that one for this one here. Let's go over to the calculator, just to make sure you understand what I'm talking about here. I'm going to go to y equals, and I'm going to put in there 2x plus 4. Of course, I'm not going to fall into my trap there. I'm going to put a parenthesis around that. 2x plus 4 divided by parenthesis 3 minus x. Zoom number 6. Now, does that seem to be a function for which the horizontal line test works? Yes. Keep in mind that it almost seems as though the TI-83 graphed the vertical asymptote there. That's really not what happened. It took the last pixel up here and connected it to the first pixel down here, but it really didn't graph the line x equals 3, which would be a vertical asymptote here. We're going to talk about that in a later section. Okay, so back to the paper, and we now know that this function indeed is one-to-one, but like I say, you don't have to worry about trying to get tricked by somebody giving you a function saying find the rule for the inverse, and the correct answer was, oh, there isn't an inverse because it wasn't one-to-one. So I'm going to put y equals 2x plus 4 over 3 minus x. Now I'm going to switch the x and the y. And now what I have to do is get y by itself on one side of the equation. That is, solve the equation for y. I'm again going to multiply both sides by 3 minus y. So I get a 3x minus a xy equals 2y plus 4. Well, this time I think I'm going to put the y's on the right side, so I'm going to subtract 4. 3x minus 4 is 2y plus xy. And I'm going to factor out a y. Y times the quantity, 2 plus x. And so finally we get 3x minus 4 divided by 2 plus x. That'll be y. Okay, so here I got a 3x minus 4 divided by 2 plus x. So I believe this function has that inverse. Now let's come back to the calculator here. I just happen to have still in y1 2x plus 4 divided by 3 minus x, and there's the function, and we're wondering, is that indeed the inverse there? One thing we could do to check is go ahead and do the composition. That would probably be about the last thing I'd want to do. To show you something, I'm going to push the graph button. There's the function. Now if I look at the buttons, right here's a button called draw. Okay, draw. So I'm going to go yellow button, draw. And it's asking me, what do I want to draw? Well, there doesn't seem to be anything really neat there that I'd want to draw. But oh, there's an arrow there by the 7. So let's go ahead and toggle on down and see what else we could draw down here. 8 is draw inverse. Here we got circles and text, and you can draw with a pen. There it went back up. Push up. There it goes back down. Number 8 says draw an inverse. I'm going to push a number 8 here. Now, here's what you got to do. You got to tell it what function to draw the inverse of. So I'm going to push here the button called vars for variables. When I push the vars button, it gives me that window. If I go to the right, I get y variables. And if I push the enter, there's y1. So in y1 on the calculator, I've got the original function. I'm going to push enter there. It says now draw the inverse of y1. And push enter. Go back to y equals. And go left arrow, left arrow. I'm going to make the original function in a thicker line. Now, unfortunately, I think when I go back to graph, I lost that inverse. I think my thinking was right. So I'm going to have to draw that inverse again. Oh, that's good. Never hurts to practice. Go yellow button, program. Let's draw. Number 8 it was. I just pushed a 8 there. Then I go to vars. Right to y vars. Function y1. Push the enter. Now those two graphs look interesting to me somehow. The thick one is the graph of the original function, and the skinnier one is the graph of the inverse. Just look at those two graphs for a little bit. They seem to be related to one another somehow. They seem to be mirror images through the line y equals x. Now you remember when we did that triangle activity there, that we reversed the x and the y coordinates and we got a graph that was the mirror image through the line y equals x? See, on the inverse, what happens? You reverse the x and the y coordinates from the original function. So of course, you get a graph that's the reflection through the line y equals x there. Now that the thing which isn't really but seems to be a vertical asymptote seems to have turned into a horizontal asymptote up there. That's pretty neat just by itself. Now I'd like to try one more thing. In y2, I'm going to put what we believe was the graph of the inverse. That's the 3x subtract 4 divided by parenthesis 2 plus x. Okay, so I'm going to push graph. X minus 4, 2 plus x. Okay, I'm going to go left, turn that one off, now push graph. So that's what we believe is the graph of the inverse. Now I'm going to draw its inverse. Oh my. Draw. Number 8. But now, when I go to vars, I want number 2. What's in y2? Oh, okay. So does this graph seem to be the reflection through the line y equals x of that graph there? Why, again, it does seem to be that. Okay, enough of that. And that finishes 2C. I don't know. See, this one is just not nearly as classy as that 55 Thunderbird was. Not nearly as classy. That finishes 3C. I think I've said 2 several times when I meant to say 3. That finishes 3C, so you're now invited to work the problems prepared for you in section 3C. (3D). Radical equations. Now I'm going to begin with an equation that's not even a radical equation, but I want to show you something. Okay? So I'm going to begin, find the solution set x equals 4. Now that would appear to be not a difficult equation to solve. It looks like the solution set is just plain 4. So now I wonder, is it legal or is it not legal to square both sides of an equation? That would be legal because, see, by squaring both sides of an equation, since x and 4 are the same, I can either multiply this by 4 or I can multiply it by x, and that's the same thing. And the right side, I can either multiply it by x or I can multiply it by 4. Since they're the same, either one is fine. So it should be legal to square both sides of an equation. Let me go ahead and square both sides of this equation and see what happens. Okay, x squared is 16. Now, the solution set to x squared equals 16 is going to be 4, but also negative 4. Now, there's got to be some point that Dave is trying to make here, and there is. Right? The point is, if you take an equation which is true, and if you square both sides of that equation, what might happen is that you might introduce some values, which indeed are values of the new equation, solutions to the new equation, but not the old one. That is, those are called extraneous roots. Those are answers that you get that don't work in the original equation. You see, negative 4 doesn't work up here. So the point of this is, watch out for extraneous roots. Most especially if you're going to square, raise both sides of an equation to a power, make sure you always check your answers, because that's a prime time when extraneous roots might happen. So let's go ahead now and solve some radical equations. Square root of x is equal to 9. Okay, the name of the game in solving equations is do whatever it takes to get just x by itself on one side of the equation. So what it would take here is square both sides. So if we square both sides, we get an x here, we get an 81 here. Since we've squared both sides, we're going to be careful to go ahead and check. And indeed, the square root of 81 is 9. The square root of 89 isn't, plus or minus 9. And so that worked okay. Now, at first you might think, the thing to do is raise both sides to the third power. However, if you raise both sides of this equation to the third power, not only do you not do yourself any good, you do yourself some bad, because you're going to get lots of other radical expressions in there. So let's see what we might do instead of raise both sides to the third power. See, if we raise both sides to the third power, we actually have a plus b cubed. We don't want to do that. Rather than do that, let's subtract 2 from both sides. Now if I raise both sides to the third power, we'll be okay. And of course, negative 2 raised to the third power is a negative 8. I guess I should be clever enough to check the answer. Cube root of negative 8 is negative 2, and negative 2 plus 2 indeed gives 0. So that checks out okay. Alright, let's try square root of x plus 3 is equal to 0. Well, now here we do not want to square both sides in this form. Instead, I want to subtract 3 from both sides. Square root of x is -3. And then we'll square both sides. And of course, -3 squared, that's not the opposite of the square of 3. That's really -3 squared. That's +9. Now let's go ahead and check that. Square root of 9 is 3. 3 plus 3 isn't 0. And so we're going to say here, no solution, or you can put that 0 with the slash, but if you remember, the computer people think that's the number 0 there. So, see, that was my big argument with using that symbol, is that somebody here who wrote, the Greek letter phi, I guess it is, it's the empty set symbol. I wouldn't know, did they think 0 was actually an answer to this equation, or did they think that there is no answer to this equation? No solution. Now, of course, you remember Erica, right? Erica, she would look at this and say, looky here, square root of a number has got to be at least 0, right? And if you take something that's non-negative and add 3, you can't get 0 for an answer. So she would have just looked at that and said, there can't be any answer to that one. But it only took 15 seconds or so to go ahead and do it the hard way. So if the hard way is just 15 seconds, it's not very hard, at least. Okay, let's try this one. X minus 4 is equal to square root of the quantity 2x. Well, it looks here like the plot is thickening some. Now we've got an x on both sides. Oh, goodness. Well, on the one hand, I can square both sides as it is. And there's no way to avoid, see, if I put the 4 over here on the other side, I'm still going to get a binomial kind of an expression squared. So we might as well just go ahead and square both sides as it is. Just thinking that there ought to be some way that we could get every student, the first time they take a math course in which the square of a binomial appears, that they get the problem right then and never miss it in any course beyond then. I wish there was a way to do that, because even my college level calculus classes, some students there are still changing this to x squared plus 16 and thinking it's right. So there's probably been 3 or 4 courses that student was losing points by not knowing how to square a binomial there. Like I say, there should be some way that we could get every student to get that right the first time they learned it. Just think how much better off they'd be. If you've got any secret methods of guaranteeing that, email them to Carmen, right? And she'll then pass them on to me. So, all right. To square a binomial, you square the first term and you take twice the product. Let me say that again a little bit slower. To square a binomial, you square the first term and then you take twice the product. So that's a -8x, and then you square the last term, plus 16. And of course, 2x, the quantity squared, becomes just 2x. Square root of 2x squared is just 2x. So it looks like we've made good progress. Not done, but we've made some good progress in that we managed to get rid of the radicals. I would think that's the first mission, is to get rid of the radicals. I'm now going to subtract 2x from both sides. X squared minus 10x plus 16 is now equal to 0. So it's now a quadratic equation in a standard form. From here, we could complete the square if we were feeling really ambitious. Or I guess if we were getting paid for doing this problem by the minute, then we'd probably go ahead and complete the square and do it that way. We could do the quadratic formula, but always, to get something done as quickly as possible, you try to factor first. You spend at least 20 seconds seeing if you can factor. a 16 and a 10 there. It looks like a 2 and an 8. X minus 2 times x minus 8. It's got to be 0, so x is 2 or x is 8. Now we did, in coming up with solutions here, we did square both sides, and so we better check. Now here again, you do not want to check x squared minus 10x plus 16, because both of those numbers are going to work in that equation, because that's past the point that we squared both sides. But I suspect that if we go back to the original equation, something might go afoul. Let's go back and check. First I'm going to try the 2. Oh, looky there. If we put a 2 in there, 2 minus 4 is a negative number, and see, the right side there has got to be a positive, so that tells me right away 2 isn't going to cut the mustard. I get a negative 2 on the right and the square root of 4, which is 2 on the left. 2 isn't working. Now what if the 8 doesn't work? I mean, that's a possibility too. If the 8 doesn't work, then we have to say there is no solution to this equation. If we put the 8 in there, 8 minus 4 is 4. 2 times 8 is 16. Square root of 16 is 4. And so 8 works. Solution set to that problem is good old number 8. Voila. Every teacher's got to decide how you grade a paper if your student submits that paper with the answer 2 and 8 in there. Like I say, everybody has to decide for yourself how you do that, unless you've got some assistant principal who says this is the way you grade that paper. The way I would grade it, I would give the student half credit, right? If there was supposed to be just one answer and they came up with 2 and didn't bother to check, I'd still give them half credit, because they still understood something about that problem. They just didn't understand everything about the problem. I'm not mad at somebody who grades a different way there. Like I say, we all have to decide that for ourselves. Solving radical equations. I think we'll try this. Cube root of x plus 10 is equal to 16. Now that 10 is not under the cube root. So the first thing I'm going to do is subtract 10 from both sides. And then I'm going to raise both sides to the third power. 6 cubed, I think that's 216, but I'm not positive of that. So I'll come to my friendly calculator. 6 to the third, it says it's 216 also. And cube root of 216 is 6. 6 plus 10 is 16. Seems to have worked okay. Square root. 6x minus 5 plus 10 is equal to 3. I'm going to subtract 10 from both sides. Square root. Ooh. Come on, Dave, you can write better than that. I'm going to subtract 7 from both, or subtract 10 from both sides. And then we notice, oh, looky there. Those of us who have our thinking caps on are looking at this equation and we're saying, See, there's no need to write down any more stuff on this one, because the square root of anything can't be a negative 7 there. So, done with that one. There's no solution there. Of course, anybody who wants to, feel free to continue working on that. I believe you'll come up with an extraneous root, and then come to a conclusion that there wasn't an answer. X minus 12 equals square root 16x. Try and see. I'm going to square both sides. So I get an x squared minus 24x plus 144 equals 16x. And so we subtract 16x from both sides. Okay, two numbers that I can multiply to get 144 and add to get a negative 40. Doesn't look real likely. Let's see, 36. Oh, 36 and a 4. I wonder if 36 times 4 is 40. I wonder if 36 times 4 is 144. It happens to be x minus 4, x minus 36 equals 0. And so at first, I believe I've got two answers, 4 and 36. Now I'm not falling into any traps here. Try the 36. 36 minus 12 is 24. 16 times 36 and take a square root. Oh my. 16 times 36 square root. It's 24. So the 36 works. Let's try the 4. Uh-oh. 4 minus 12, that's a negative number, and there's no time I know of that a negative number can equal a positive number, so the 4 was one of those extraneous roots, and so we're not going to settle for that kind of stuff. Well, we'll try one more real quick. Square root 2x minus 1 equals square root x plus 4. Now, what on earth? I guess we'll square both sides, keeping in mind that since we've squared both sides, we are going to check any answer that we might get. I'll subtract the x, add a 1, see if 5 works. 2 times 5 is 10, 10 minus 1 is 9, square root of 9 is 3 on the left. 5 plus 4 is 9, square root of 9 is 3 on the right. It worked. So it doesn't happen that every time you square both sides of an equation you get some phony answers. That doesn't happen every time. It's just that you want to check every time because you never know when things were okay and when things weren't okay. Well, now that's everything I know about radical equations, and so you can now enjoy the problems in section 3D. (3E) Graphs of radical functions. Let's first try y equals the square root of x, and I'm going to resort to making this old chart. I guess I could have done it with the calculator, but what the heck. Let's go ahead and make this famous old chart. Pick the x and find the y. Now, it won't do us any good to pick negative x's, because anytime you graph, it's strictly the set of real numbers. So we don't want any square roots of -1 there. And I'll start with a 0 and a 1 and then a 4. Now, notice that I'm picking the x coordinates here pretty expeditiously. That is, those numbers which are perfect squares. A 9. So the square root of 0 is 0, square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. And let's go ahead and plot those points. We got 0, 0, 1, 1, 4, 2, 9, 3. Now we notice that this graph is going to grow very slowly, because look at here. From 4 to 9 was a distance of 5 units that way, and we only got 1 unit higher. From 1 to 4 was a difference of 3 units, and we only got 1 higher. Now, how long is it going to take us to get 1 higher again? We'd have to go all the way to 16, 7 units to increase by 1 again. So although this graph is going to continue to increase, it's going to increase pretty slow. So it looks like there's the graph of the square root function. It has a limited domain. Those values of x that are 0 and more. And let's go ahead and graph the cube root function. And I'll just do this mentally. If I put in 0, I get out 0. If I put in 1, I get a 1. If I put in -1, I get a -1. Now, if I were going to graph this function based on those 3 points, I might even try to draw a linear function there, but I'm not going to be foolish enough to do that. I mean, 3 points might be enough if you're drawing a line. I guess the next number I'll put in there is a 8, and the cube root of 8 is 2, so I have to go all the way to the right 8 until I get up to 2, and the cube root of -8 is a -2, and so like so. Let's go over to the calculator and see if it's agreeing or disagreeing with what we've got so far. Looks like y equals, get that junk out of there. Here we're going to want to zoom. Number 6, I guess, is standard. Y equals, first let's try the square root function. Square root x. Look at there, remember that last parenthesis graph? It looks pretty much like the shape that we came up with. Now let's try the cube root. Oh, I guess I'll get fancy and find it here. Cube root's number 4. Cube root of x. Graph. Pretty much what we came up with. Now, of course, we know that if we were doing a 4th root, it would look more like the square root in that you couldn't have negative x's, and if we were doing a 5th root, it would look more like the cube root because you could then have the negative x's. So even roots have a restricted domain, and odd roots don't have a restricted domain. Now let's come back to the paper here and do some remembering. On the one hand, a long time ago now, we had graphed y equals x squared, and things like y equals x minus 1 squared plus 2. And there we had the characteristic shape of that parabola. X minus 1 squared plus 2 has exactly the same shape but a different location, right 1 and up 2. Now there was nothing special about the squaring function. If we knew the graph of x cubed, x minus 1 cubed plus 2 would be that identical graph moved 1 to the right and up 2. If we knew the graph of the square root of x, square root x minus 1 plus 2 would be the same graph moved right 1 and up 2. So, knowing that, let's graph Okay, now when we first see this, we're thinking square root graph. Actually, it's a half of a parabola, a sideways parabola. But instead of being a parabola emanating from the origin, this is going to move right 1 and up 2. So that first point would be there. And from there, I'll draw a graph of the square root function. That seemed too easy. Let's go to the calculator. See what's happening there. Clear. So I'm going to do square root x subtract 1, put a parenthesis, add 2, graph. Well, what do you know? They seem to be agreeing. Cool. Four times the cube root. Look at what I've got written on this paper here. All right, now I want you to just think about the way I've written that down for a second or so and see it in your own mind. Do you see any possible ambiguity in the way I've written that down? Because, you know, at first I thought my writing was kind of going to cut the mustard there, but at last I see that this was not a good way to have written that one down there, because somebody looking at this might ask, is this 4 to the third multiplied by the square root of x plus 2, or is this 4 times the cube root of that? So I think I'll be a little bit clearer and write it down like that. I suffered for many years having students come up many times during a test and asking me what the test said. Now, this is back in the old days when we did those purple machines, the mimeographs, and I would hand write tests and all. I'd be embarrassed today to show you a test that I gave 10 years ago, because not only were they sloppy, they were so sloppy that often you really couldn't read them. I mean, you've noticed already that my handwriting is not the best in the world, and I'm trying to be careful now and write pretty nice. And then a few years ago I learned how to use this thing called math type, which is the computer thing that makes up tests that students can actually read. I have to say now, when I pass out a test, I'm proud of the way those tests look, because it looks like some test that I got from a book. Really, really look nice. So if I had math typed this one, it would have been very clear without the parenthesis. Oh well. It's going to be a cube root graph. Now, which way are we going to go? Right 2 or left 2? I think we go left 2. And I think we don't go up 4. Right? It's going to magnify the graph by 4. It's going to be a cube root shape. I'm going to make this a little steeper than normal since everything's getting multiplied by 4. Okay. Just came apart a little bit here. See, now that's really bad, because you weren't supposed to know that that microphone was there. Well, I suspect you already knew there was a microphone there anyhow, so it wasn't all that bad. Well, that was a mighty short section there, but that's everything I know about graphing radical equations. And so, since that was a short section, we'll do the short car there. No, I can't see myself driving a car like that. It's that 55 T-Bird now, that's a classic. I could see myself driving that car. You can now enjoy the problems in section 3E. F. Exponential growth and decay. First thing we need to do is graph some exponential functions now. I think I mentioned this a few sessions ago that it's a bad word to say an exponential function. A normal person hearing somebody talk about an exponential function would of course think that an exponential function is a function that has an exponent, and not so. If we come to the paper here, we see an exponential function is a function like 2 to the x power. That's an exponential function. It not only has an exponent, but the variable appears as a part of that exponent. So there's an exponential function. Now I'd like to graph that one. Okay, so 2 to the x power. I'm going to pick here 0, 1, 2, 3. So 2 to the 0, and of course that means 1. 2 to the 1, and of course that means 1. 2 squared is 4, and 2 to the third is 8. So I can plot those points. I'll go ahead and do that on the side here. I got 0, 1, 1, 2, 2, 4, 3, 8. This graph seems to be rising rather steeply. And if you think about it, well, it appears as though every time you increase x by 1, the y-coordinate doubles. And if you think about it, of course that's true because this is 2 to a power. So if you increase the power by 1, you get twice as much as you used to have. Let's try the negative side. Negative 1, negative 2. Here we've got 2 to the negative 1 power, and of course that's a half. Then we want 2 to the negative 2 power, and of course that means 1 over 2 squared, or 1/4. And so I get negative 1, 1/2, negative 2, 1/4, and every time you step to the left one, you get half as much, producing a horizontal asymptote. Horizontal asymptote. I don't know the origins of the word asymptote. I wish I did. That's another thing I've been wondering about. I don't know what language asymptote came from. If any of you know, email to Carmen and she'll tell me where asymptote came from. And seriously, I would like to know. But right now I don't. Okay, there's 2 to the x. Now, suppose I did f of x is 3 to the x instead of 2 to the x. Do I believe that 3 to the x would have the same kind of a shape as did 2 to the x. Well, let's investigate and find out. Again, pick a 0, 1, 2, 3, x, y equals 3 to the x power. 3 to the 0 is 1, 3 to the 1 is 3. 3 squared is 9, 3 cubed, 27. 3 to the negative 1, that's 1/3. And 3 to the negative 2 is 1/9. 0, 1, 1, 3, 2, 9, 3, 27. Seems to have the same kind of a shape, only steeper. Now, I don't know how good a job I've done with my scales and all that, so let's go to the calculator. It can probably do a better job anyhow. See what good old TI-83 has to say over here. I'm going to get that out of there. So here I'm going to put 2 to the x power. And down here, now I'll tell you what, I'm going to make this a little bit darker. I'm going to put 3 to the x power. We'll do the graph. So 3 to the x indeed is steeper than 2 to the x. Now you can't see it well here, but the 3 to the x is closer to the x-axis than 2 to the x is back there. We'll investigate that in a second. Let me just make a comment first. It seems as though these graphs are the x-axis. I mean, that's the way it appears. Now, once again, technology is very nice, not perfect. You understand that what the calculator does, it fills in squares that are called pixels right there. So, like if I had a checkerboard and wanted to draw some kind of a line that ran not exactly horizontal, you see, I'd have great difficulty doing that because, you know, what squares am I going to fill in on that checkerboard there? That's what's happening here. Now, I'm going to push this zoom button. Number 2 says zoom in, so let's go ahead and push number 2. Then I'll push the enter. Oh, so now we can see it a little bit better that 3 to the x is above 2 to the x on the right side for positive x's, but 3 to the x is below 2 to the x on the left side. Of course that makes sense because here we have 3 to a negative power as opposed to 2 to a negative power. So of course the value is going to be smaller. Let me try to zoom in on that again and see if we can get it a little bit better. Zoom 2, enter. You know what I did there? I zoomed too much. Change that window a little bit. Y max. I want to get some bigger y coordinates. Well, I'll try a 2, see what that looks like. Looks like I'm zooming too much. The first one almost appears to be linear, and of course we know that it's not. Okay. I guess we've made the point there. Zoom 6. Back to standard. And we know that is not the x-axis there. Exponential growth and decay. Okay, these would be examples of functions that are exhibiting exponential growth. Now, somebody told me, I don't know if it's the truth, but somebody told me that there's a sad fact that populations grow exponentially. So if you look at the population of the world, it's growing exponentially. But this person told me that the ability to sustain a population only grows linearly. If that's true, let's see what that means. Come down to the paper here. Let's suppose that we had some world population that's growing exponentially, and we have an ability to sustain a population that grows only linearly. By sustain, I mean find food and water and enough air and elbow room and everything like that that it takes to have a life. Now you see, the reason that that's a sad fact is no matter what line I might draw here, this exponential curve, of course, you know, goes really fast. No matter what curve no matter what line I draw here, the exponential curve eventually gets bigger than the line, unless I were to draw a vertical line. But of course, that's not going to exist there. So if we have a situation, here is population, here is the ability for that population to be sustained. At some critical point right here, what happens is that the population has exceeded the ability to be sustained. Now when that happens, what does that mean? Somebody goes hungry, somebody doesn't have the ability to sustain itself. Now, of course, you know that drive to sustain yourself is a very strong drive. So if you're this country here that doesn't have enough food to feed itself, and you see your neighbors there have enough food, I mean, you know what's going to happen there. Those people are going to say, let's go get it. And then, then you have a war. So the person who was telling me about all this stuff said wars are just cyclic, that, every now and then you're going to have a war, but it's because of this situation right here. I don't know if I subscribe to that or not. It could be. Let us graph. Let's come back to the calculator here and do one kind of a quick thing. Clear, clear. Instead of doing 2 to the x, I'm now going to do 0.5 to the x power. Now I wonder how that graph might compare. Sketch the graph. Oh, now that's kind of neat. It looks like the graph of 1/2 to the x is going to run down the hill instead of running up the hill. Well, we'll need to investigate that a little bit more. So much for that tape. Let's go back to that calculator and continue that investigation. I think I noticed something that might bear watching. We had graphed 1/2 to the x. Got that graph. In y2, I'm going to go ahead and put 2 to the x power. And I like to graph these two at the same time, or on the same axes. Now, what do we notice there? Why, my goodness, it looks like 2 to the x is the reflection through the y-axis of 1/2 to the x. And that, in fact, is the case. And 3 to the x would be the reflection of 1/3 to the x, and, they come in pairs like that. Okay. So let's make a comment here. In y equals a to the x power, first thing to observe is that if a is bigger than 1, then you're going to get a graph that increases from left to right. Of course, the y-intercept is going to be 1. The domain would be the whole set of real numbers, and the range would be just the positive numbers, not including 0, because you never get down to that x-axis there. If a is between 0 and 1, Then you have a function that decreases from left to right. Still has a y-intercept of 1. So the domain of that is still going to be the whole set of real numbers, and the range of that, again, is 0 to infinity. Well, now you might be wondering, what are the other possibilities? For example, what if a is the number 1? Well, 1 to the x power is going to be just 1, and so that would be just a horizontal line, not a very interesting exponential graph, so we don't really consider that. Then you might say, well, what if a is a negative number? Well, it turns out that a to the x is undefined too many places if a is a negative number to make it interesting. For example, if a is negative 4, when x becomes 1/2, you see that's undefined. Right? When x is 1/4, that's undefined. When x is 3/4, that's undefined. So a to the x would not be defined too many places if a is a negative number, so we don't consider that. Thus, what we've got on the paper is a complete treatment of the exponential graphs, exponential growth and decay. Of course, if a is greater than 1, that's when we get growth. And if a is less than 1 but positive, that's when we get decay. Let's practice a little bit on just graphing. And we'll try to do these with brain power if it's not too hard to do so. 3 to the x and then subtract 1. That subtract 1 is not in the exponent. Well, this is going to be the graph of 3 to the x moved down 1 unit. Now, if it was just 3 to the x, come like this. If I move that down 1 unit, what we're going to get is a horizontal asymptote. Y equals -1. Now, to find the y-intercept there, what I did is I put a 0 in. So 3 to the 0 is 1. 1 minus 1 gives 0. And so there we have it. Y equals -1. Well, how about if we tried to graph y is 1/2 to the x minus 3? Now, this looks like it's getting a little bit on the nasty side. Because the base there is a number less than 1, we know the graph is going to run down the hill instead of up the hill. If I put a 0 in there, I get 1/2 to the -3. Now let me stop and reflect on that a little bit. 1/2 to the -3, that would be the same as 2 to the 3rd. Yeah. Okay, and 2 to the 3rd is 8. So now we get a y-intercept of 8. Since it's a base of 1/2, going to move that way. So that would be an exponential decay problem. Oh, let's try one more anyhow. Now, we've talked about this before, a long time ago. If I were to graph y equals the opposite of 3 to the x, that is not the same as the quantity -3 to the x power. Of course, that -3 to the x power would not be defined too many places. This would be 3 to the x, but flipped upside down. Now, 3 to the x would normally come up here. So if I flip that upside down, looks like I'm then going to go down the hill instead of up the hill. Now, I'd like to find the y-intercept, and so I put a 0 in for x, and I get a -1. So -1 is the y-intercept. And that's what I know about graphing exponential functions. And so that ends session 3, section F. You can work those problems. It's not a whole lot there. Shouldn't take you more than 22 hours to get all those problems. Oh, I was kidding. It shouldn't take you more than a few minutes to work those problems in section 3F. The next section is going to be a little bit on the long side. Not a lot on the long side, just a little bit on the long side. You'll like it. Session 3, Section G, the ubiquitous number E. This word ubiquitous means appears just everywhere. Ubiquitous number E. So this E pops up in the strangest places. E is chosen to have been E in honor of the Swiss mathematician Leonard Euler. Now, Euler spelled his name E-U-L-E-R, but it said Euler. A very prolific mathematician, and they've named E in his honor. So, pi wasn't named in anybody's honor. There's another thing I don't know. Where on earth, why was pi chosen to have been pi? I'm sure it has nothing to do with cherry pies or apple pies or anything like that, but if any of you know why pi was chosen to have been pi, email to Carmen and she'll let me know about that. I think I'm going to wind up learning a lot from this course here. That's good. Ubiquitous number E. E is approximately 2.72. It's one of those irrational numbers, as is pi. And so why was approximately, I meant to put approximately there. I had an equal sign there. I want you to note that I changed it to approximately equal to because E is an irrational number. Why would someone choose 2.72 roughly to be a special number? If I could give you an adequate explanation of that in an Algebra 2 course, I promise you I would give you that adequate explanation of why roughly 2.72 was chosen to be a special number. But in an Algebra 2 course, I can't, or at least I don't know how to present any justification for having chosen a number like that and then saying that it's special. The reason for that lies in calculus, that there's certain things you do in calculus called derivatives, and for exponential functions, those derivatives are particularly nice if you use E as the base of your function, and if you don't use E as the base for your exponential function, those derivatives are a little bit more difficult to do. So you're going to have to wait a few courses until you find out why E is special. For now, you're going to have to take my word for it. Alright, so let's see if we can graph y equals e to the x power. Since the base there is, in fact, greater than 1, we know it would be an exponential function increasing, and of course with a y-intercept of 1. The domain would be all the reals, and the range would be the open interval from 0 to infinity, that is the positive numbers. So no matter what number x is, e to the x has got to be a positive number. Okay. Well, I guess first we'll do a little bit of simplification. I want to simplify 3 times e to the negative 2 power times e to the 6th. Now, the rules for exponents continue along. Just because the base here happens to be an e doesn't mean that the rules are going to be different. So when you're multiplying and you have the same base, the thing that you do is add the exponents. So this would simplify to just 3 times e to the 4th power. Yeah? That's all there is to that. E to the 4th divided by 2e. Well, same. There's an exponent of 1 here that's not written. So 4 minus 1 gives 3, and I could write this as e to the 3rd divided by 2, and I don't know what else I might do with it beyond there. That looks pretty good. Just for completeness, if we ever need it, let's make sure we can evaluate one of these. So let's write 2e to the 4th accurate to 3 decimal places. Okay, let's go to the calculator. Turn it on. I guess I'll get these things out of the y equals there. Though we didn't have to do that. But all right, 2 times e to the 4th. Now on the one hand, I could go ahead and substitute in there that 2.72 for e, but on the other hand, I don't want to do that. There's 2 places that you can get the e. So here I look on my divided by, and divided by above there is a e, so that's one place that I can get the e. The place that I think is a better place to get the e is over here above ln. It says e to the x power. I think that's a better place to get the e, and I'm going to show you why. We would like to compute 2 times e to the 4th. So first I push the 2, and then I go yellow button e to the x, and let me look at the screen here. See, now if I do it that way, all I did was push the e to the x button, and the calculator is asking me what exponent do I want to put in there. And so I put a 4, and then I just push the enter. All right, so accurate to 2 decimal places, I'd say would have to be 109.20. Oh, I did say to 3? Oh. Since I had said to 3 decimal places, we'll write 109.196. 196. Okay. Yeah, 3 decimal places. Okay, now we could do that using the other e. Let's go ahead and do it that way. I'm going to compute now 2. So I push a 2. Now I still have to push the yellow button to get that e. But if you look at the screen now, what I have to do is put the caret in there. Upper 4. And I'm getting the same answer. But I've often wondered why on earth they put this second one over here, because really the only one I ever use is the one above the ln, because it already tells you to put the exponent in there, and that seems most convenient to me. But they're both there. Use either one as you so choose. Applications. Let's talk about money at compound interest. I guess it's probably a prime application of exponential functions. Money at compound interest. First, let me talk about what we mean about compound interest. Let's suppose I take $100 and deposit it, and let's suppose I'm going to get 8% interest. Compounded annually. So right now, at time equals 0, got $100. We're going to put that in the bank. And here it is, 1 year. T equals 1 year. And so I wonder, how much money do I have at the end of 1 year? Well, since the interest rate is 8%, I started with $100. 8% of $100 is $8. So at the end of 1 year, I've now got $108. When I was a small child, a few years ago, in the savings accounts, they used to actually call these a passbook savings account. And if you took your $1.25 over to the bank and said, I wanted to start a savings account, they'd actually give you a little booklet, and that booklet was the record of your account. And you could go over there, every so often and have the teller actually compute the interest. And the teller at the teller stand right there would do one of those adding machines that had the handle there and actually compute the interest by hand and enter it into your book for you there. Now, if the interest is compounded annually, the big disadvantage to that is if you put $100 in the bank and get 8% a year, and if you go there 364 days later and ask to withdraw your money, the only thing they have to give you is $100, because if this is compounded annually, they don't have to pay you any interest until the end of the first year. So for that whole 364 days, you didn't win any money there. Nobody I know compounds interest annually anymore. But let's suppose instead, this is compound annual. Let's suppose instead that we compound that interest semi-annually. So at time 0, we've got $100. So at time a half, let's see how much we've got at time a half there now. Okay. Now if we compound this at a half a year, I'm not going to get $108 halfway through there, right? Even though the interest rate is 8%, that's 8% per year. And so how much would I actually get at the end of 6 months? Actually in the account would be just $104. Yeah. Now what's going to happen? For the second 6 months of that year, when I'm drawing the 8% interest, I'm not drawing 8% interest on $100. I'm now drawing 8% interest on $104. Yeah? So I also get the 8% of the $4. I guess that would be another 32 cents. So at the end of 1 year, I would now have $108.32. $108.32. So the more often that you compound the money, the more money you get to have. Yeah? I got an extra 32 cents here just by having them compound the interest in the middle of the year. Now you see what happens here. If you compound that quarterly, then from month 3 through 6, you get the interest on $102 instead of just getting the interest on $100 there. And here you'd get the interest on that $106.16 or whatever it would turn out to be. That wasn't quite right. So the point is, the more often you compound the interest, the more interest that you get to make. Now, back when I was a whippersnapper there, banks didn't have the technology to compute compounding very often. So my best recollection is that my bank used to compound the interest quarterly. So you could go over there, you could take your $1.25 and go over there every 3 months and ask the teller to compute your interest for you there, and they'd do one of those things that you push the button and pull the lever and enter your interest in there, and on $1.25 then you had $1.27 instead of $1.25 or something like that, and you just think, oh boy, I'm getting rich now. Today, the technology certainly exists to compute the interest compounded not annually, not semi-annually, not quarterly, not daily, not hourly, but continuously. Now, believe it or not, when you move from a discrete compounding to a continuous compounding, that then gives the E function. Let me write that down here. The ubiquitous number E pops up in the strangest places. My oh my. Money at an annual rate R% compounded continuously. If A is the amount, and by that I mean the amount in the account, A is given by A naught E to the RT, A naught, the amount at time 0. In other words, that A naught would be $1.25 in my case there. That's how much money you put in there. R is the interest rate, and T, of course, is time. And that time will be in years. Now, rather surprisingly, this one formula right here is going to work all the problems for us in exponential growth and decay. One formula works every question. So it actually turns out, as far as the math is concerned, whether you take money and put it into a savings account at compound interest, or whether you take some radioactive element and are investigating how much radioactivity remains, or whether you're investigating population growths, it's all the same function. Goodness, that is surprising. So, I've got here some questions. Uh-oh, these look like word problems. Now, the reason that these look like word problems is they are word problems. So that's why they look like it. So let's go ahead and find the interest on $1,000 at 4% for 6 years. Find the interest on $1,000 at 4% for 6 years. Well, we do know that the amount is going to be A naught E to the R times T. All these problems are just a matter of putting the right number in the right place. Well, once we find the amount, we can subtract the original $1,000, and that would give us the interest. So let's say A is going to be $1,000. That's the A naught. That's how much we started with. Times E to the R times T. The T is going to be 6 years, and the R is 4%. Now you got to be careful here. If I put down here 4, I'm not putting down 4%. I'm putting down 400%. And unfortunately, you aren't getting any 400% here now. So what I've got to do is put 0.04. 4% is 0.04 times 6. Now I'm going to go ahead and compute that. And since I'm not the teller at that window with that old mechanical calculator thing, we'll use the TI-83. So I'm going to put 1,000 times E, and there again I'm going to use the one that's above the LN there, to the 0.04 times 6. Oh, it's a 9. Nice feature of the TI-89 is I can backspace that and just put a 6 there and then put a parenthesis. Now before I push the go button here, let's stop and reflect upon this. Looking at that, that appears to be the correct answer. I mean, I'm taking 1,000 times E to the 0.04 times 6. That appears as though it should be the correct answer. Let me push the enter button and see if the answer seems reasonable. Oh my goodness, we've now got $6,244.86. That answer doesn't appear to be reasonable. Let me try that again. 1,000 times E to the 0.04 times 6. At first sight, there appears to be no difference between this calculation and this calculation, but there is a big difference. What the top one did, it computed 1,000 times E to the 0.04. It found the answer to that and then multiplied that answer by 6. And that's not what we wanted it to do. So this one will take 6 times the 0.04 and make that as the exponent. If I push the enter there, that seems a lot more reasonable. Okay. So if I come back to the paper here, it tells me that the amount in the account is now 1,271. And if we round that off to hundredths, 25. Now be careful, that is not the answer. So the interest is going to be just $271.25. Now, you know, if one of my students told me that the answer was $1,271.25, I'd have to give them a little bit of credit for knowing the formula and knowing how to push the buttons correctly on the calculator and all that. But I'd have to take a little bit of points there, too, for not reading the problem carefully. So word problems, as always, the last thing you should do is go and read the problem again just to make sure you've answered the question that was asked. All right, number 2. Sally deposited $2,500 into an account paying 3% per annum. By the way, the only kind of compounding that we're ever going to do is continuous, so everything we're going to do is going to be the E function there. 3% per annum. If she leaves the money there for 5 years, how much will be in the account? Now we're assuming, of course, that we didn't come and add anything to it other than the interest, and we didn't come and subtract anything from it either. Okay, how much will be in the account? Well, once again, the only equation that we're going to need here is that A is A naught E to the RT. And so we started here with $2,500. 0.03 times the 5 years. I'm going to come over to the calculator and compute that one. So now 2,500 times E to the 0.03 times 5. So my observation has been that if you use that times instead of a parenthesis, you get the answer more often than not. Push the enter. I've now got 2904.58. 2904. And if I round it off, it's 59. Now this question said how much will be in the account. It did not ask for the interest, so I do not want to subtract the $2,500 that time. Right? It says how much will be in the account. All right. So there's that one. Question 3. How long will it take a sum of money to double at 6%? How long will it take a sum of money to double at 6%? So that means if I start with $1, I want to wind up with $2. And if I start with $50, I want to wind up with $100. It turns out that it would take the same amount of time at the given interest rate. It would take the same amount of time for $1 to turn into $2 as it would for $50 to turn into $100. So you can do that anyway. If we come to the paper here, the amount has got to be A naught E to the R times T. How long will it take a sum of money to double? What I was talking about, see, what I can do is I can put $2 here and $1 right there. Or I can put $100 here, $50 right there. Or, you know, I can put $2 million here and $1 million there. Since I'd like to do this as efficiently as possible, I'm going to start with $1, so then I want to wind up with $2. The interest rate is 0.06. T is the time. We're now looking for the time. Now, in order to solve this as a manipulation, we would have to use a thing called the logarithm that we haven't talked about yet. So we're going to take another approach. See, if I had put 100 here and 50 there, the next thing I would do is divide both sides by 50, and now I'd have this equation anyhow. So that one is nice right there. Here's what I'm going to do. I'm going to come over to the calculator, get all that stuff out of there. I'm going to go to y equals, and then y1, I'm going to put e to the 0.06x. 0.06x. I'm going to graph that function. Okay. And then in y2, I'm going to put 2. Graph that one. Now, what we're looking for is a value of x for which e to the 0.06x is equal to 2. Right? So I'm trying to find out where y1 becomes the same as y2. Looking at this graph, it looks like I'm going to have to change that window a little bit because it looks like it's over here somewhere. So let me increase that x max to a 20. That looks pretty good. So I'm looking for a point of intersection. I guess I could do trace. Let me do the calculate instead. Number 5 was a point of intersection. There's the first curve. Push enter. Second curve. Push enter. Take a guess. You move the spider to as close to the point as. Push enter. Now that says about 11.5 for x. That x is our t, and the y it says is exactly 2. And so it looks like t would be about 11.6 years. Now that's a doubling time. That's pretty awesome. What that says is that at an interest rate of 6%, it takes about 11.5 years, 11.6 years, for a sum of money to double. That means if the inflation rate in our country was 6% a year, every 11 and a half years, your salary has to double just to keep up. That's not to increase your standard of living. That's just to keep up. And that's why inflation is so dangerous, because the salaries don't increase at the same rate as the inflation does. Right? So you wind up losing money in the long run. Recently, we've been so fortunate in this country that the inflation rate has been so low, people don't even talk about it anymore. But when I first started teaching, the inflation rate was running about 12% or so a year. And see, at that rate, every 5 or 6 years your salary had to double, and of course it wasn't. All right. Well, let's go ahead and work another exponential growth or decay problem. Question number 4, it says, find the present value of a bond that matures in 8 years at 3%. Find the present value of a bond that matures in 8 years for $2,000 at 3%. What does that mean? I'm going to draw a picture here. Here's what that means. Present value. That means right now. In 8 years, that bond is going to be worth $2,000, and the interest rate is 3%. In other words, you go into your bank and you say, 8 years from now, I want to walk out of this bank with $2,000. How much money do I have to give you right now at this 3% rate in order to be able to walk out with $2,000 8 years from now? Right, so the banker does some figuring there and says, well, right now you have to give me this amount of money. We'll put that money in a bond, and that bond will mature in 8 years and give you the $2,000. So that's what we're looking for here. How much money do we have to have right now? Good news is, one equation works every problem in this section. A0 times E to the R times T. Okay, so now we're looking for the A0, aren't we? We're looking to make $2,000 to be A0 times E to the 0.03 times the 8 years. Well, I guess to get the answer here, we'll take 2,000 and divide it by E to the 0.03 times 8. Let's go over to the calculator, get rid of some of this stuff here. Y equals alright, so now I'm going to take 2,000, divide it by E to the 0.03 times 8. Push the enter. One five seven three point 26 is the A0. So you go into the bank today with $1,573.26. You purchase that bond, let it grow there for 8 years, and in 8 years you walk out with $2,000. That's present value. Okay, number 5, we're going to save until we do some logarithms. And number 6, we'll save until a little bit later too. 5 and 6, we're going to come back to those. I'm going to put those aside here so I remember to do them. At my age, you don't remember everything quite so long as once you did. want to do one more application with exponential growth. This is a kind of a neat one. This is a true story. And it's about the DeHavens. Okay. If we can look down at the paper here. Okay, the DeHavens. Looks like George Washington there and some money. A true story. Uh-oh. Don't know if they're going to be able to zoom in on that close enough that you can read it, but if you can't read it, it's okay, I'll read it to you. I don't think they can get that any better. Should have done it in a bigger font. We'll make do. If you were offered a job paying 1 cent per second, would you take it? Now, let's stop and reflect on that. Somebody offers you a job and says, well, we'll pay you a penny a second. Would you take the job? Okay, so think about that for 15 seconds and let me know what you think. You want a job that pays 1 penny per second. I guess probably what we'd want to do is like try to figure out how much that pays an hour or something like that, huh? Because I mean, nobody really ever offers you a job that pays a penny a second. Okay. Anybody take it? Raise your hand if you would take it. Raise your hand if you would not take it. Well, I didn't see anybody. No. Well, let's go to the calculator and figure it out. On. Get that junk out of there. Okay, we're paying 1 penny per second. So if I take 1 times 60, that would be 60 cents a minute. Now, how many minutes in an hour? 60, right? So I'm going to take that times 60. Oh, goodness, 3,600. Now, 3,600 is a pretty big number, but that's pennies, right? So that would be $36 an hour. Okay. Would you take a job that pays $36 an hour? Most of us probably would, because $36 an hour, that's pretty good money. And it says here, looking at the paper, next thing it says is, yes, it's legal. All right, so this is a legal job that pays $36 an hour, and most of us are thinking, that's a pretty good job. Now, for a high school student, you know, every high school student that I know would take a job paying $36 an hour, and many of them, whether it's legal or not, they would take that job. Okay, so you agree, 36 bucks an hour is good money, right? Let's keep that in mind. $36 an hour, good money. That's a penny a second. Now here comes the story, which is a true story. In 1776, a wealthy Philadelphia merchant named Jacob DeHaven lent the Continental Congress $450,000 to support the troops at Valley Forge. Now, $450,000 back in 1776 was big money. Well, actually, as far as Dave Oberly is concerned, $450,000 today is big money. But back in 1776, $450,000 was really big money. Right? Apparently, we never repaid the loan. So this Jacob DeHaven gave the Continental Congress $450,000. We never paid him back. Jacob's ancestors have filed suit seeking repayment of the loan. So apparently they found some paperwork or something that they had grounds that they wanted the government to pay back the loan. Well, I mean, $450,000 in today's world, you know, that's nothing. Who is it? Everett Dirksen, I think, one of those politicians who said, you know, you take $1 billion here and $1 billion there, before you know it, it starts to add up. But here we've got $450,000, and his ancestors have filed suit seeking repayment of the loan plus interest at 6%. So they claim that the prevailing interest rate for all those years has been 6%. You know, some years it was more, some years it was less, but that's what they want, is 6% interest, compounded continuously since 1776. Should we pay? Let's investigate. Well, I don't know. Let's see. Suppose you were in charge of making this decision here. Would you want to pay back the DeHaven family for that $450,000? I mean, it seems like a legitimate claim. I don't know if there's a statute of limitations on paying back a loan like that. And actually, I don't know if Jacob ever intended to be paid back, but I wasn't there. Let's investigate. Fortunately, this equation works every problem in this section. Now the A naught is at $450,000. E, the interest rate they want is 6%, so 0.06. And now I got to wonder, today is 2003, and so how many years has it been from 1776 to 2003? Gee, I can't figure it. Once upon a time I used to be able to do that kind of stuff just by hand, but that was a long time ago. Alright, that's 227 years. So here we'll put 227. Okay, well, let's go ahead and compute that. 450,000 times E to the 0.06 times 227. Okay, I think I got everything okay there. Now, 1776, that was $450,000. Well, look at there. It's only $3.70. Now, that's not bad at all. Gee whiz. The guy gave us $450,000. We give him $3. Uh-oh. There's an E over here with that 11. I wonder. Oh, that's scientific notation. So this is 3.7 times 10 to the 11th plus a few more bucks that we're going to ignore here. Right? So let's come over to the paper here and see what that looks like. 3.7 times 10 to the 11th power. That came out in scientific notation. Now that's 3. If I wrote 37, that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Oh, that's how much money we owe those people now. Let's put some commas in there. Comma in there. Comma in there. Comma in there. Is that billions? I'm not used to seeing numbers that big. Yeah, that looks like $370 billion is what we owe those people now. Should we pay them? Gee, I don't know. I'm glad that, people on my salary level don't have to make decisions about whether we should pay those people back the $370 billion. Somebody else has got to make that decision. I don't know what's fair. It seems fair that when somebody lends you some money, you pay them back. But that was a long time ago, and I seriously don't think that Jacob really intended to get that money back. I think he just said, here's some money to help the troops out at Valley Forge. Anyhow, let's do a little more calculation on this. I wonder if we could figure out how fast the interest is mounting up on this loan. How fast is the interest mounting up on this loan? A similar investigation, by the way, back in 1624, I believe it was, Peter Minuit bought Manhattan Island for $24 in trinkets and beads and stuff. You take that $24 and run it through at 6% over all those years and see what Manhattan might be worth today. I have no idea what Manhattan Island might be worth today, but that would be an interesting thing for you to investigate. Okay, let's go back to the calculator here now. That's the amount of money that we owe them right now. What I'm going to do is subtract from that. So I just push the blue subtract button, and notice again it says answer, and then we're going to subtract something. So it's taking that 3.7, all that stuff, and now I'm going to subtract from that 450,000 times e to the 0.06 times 226. Now let's stop and think about what I'm doing here. We took the amount of money the government owes the DeHavens now, and I'm subtracting the amount of money that we would have owed a year ago. So if I do that, the answer to this is how much interest has mounted up in the last year. Okay, so I'll push the enter for that. Oh goodness, that's the amount of interest in the last year. That e to the 10th there, it looks to me like that's going to be about $20 billion in interest that we've paid in the last year. Now if I take that and divide it by 365, then I'll have the amount of interest in a year, in a day rather. Here we switched back from scientific notation. Let's put some commas in there. Comma, comma. It's $59 million a day. Now, of course, you know, I'm doing some estimation here because the first day would have been a lot less than the last day of that year because that's the way compound interest works. But let's do it just on average. $59 million a day. I'm going to divide that by 24. So that's the interest per hour. There's $2.5 million an hour on this loan. And I'm going to divide that by 60. $41,000 a minute divided by 60. Okay, so the DeHavens are making almost $700 a second. Now, a few minutes ago, I asked you a question. If somebody offered you a job paying 1 penny a second, would you take it? And after a little bit of reflection, we all agreed that most folks would say, yes, I would take a job that pays 1 penny a second. Look at here. These people were making $683.41 a second, and they didn't even have to work for it. That's a pretty good deal. Now, we'll finish off section 3G with the good news. Here's the good news. And the good news comes in fine print. The good news comes in fine print. I'm pretty sure she's not going to be able to... Oh, look at there. That's a good producer. The good news is the DeHaven ancestors are willing to settle for a statue of Jacob. So instead of getting this $700 a second, they just said, build us a statue of Jacob. And can you believe it? Over several years now, our government has not agreed to give those people a statue of their Jacob DeHaven in exchange for this billions of dollars that we owe them here. There's got to be a reason. They're probably worried about some sort of a legal precedent or something like that. But a couple of years ago, I had a student in my night class who was studying this very problem in his economics class, and he said as of then, the lawsuit had still not been settled, and it had been on file for several years then. So the government had been unwilling to settle the case. I don't know why, but I mean, if I was in charge there and the people came to me and said, well, we'll be willing to settle for a statue, I would say, how big a statue do you want? Where would you like me to put it? How many statues of Jacob would you like around somewhere? Because, I mean, really, this is pretty ridiculous. And so on that note, a classic problem deserves a classic finish. And so we have now finished session 3, part G, the ubiquitous number E. I know you'll enjoy those problems that Carmen has selected for you in that section. And so we're in session 3, part H, which is logarithms. Session 3, part H, logarithms. Well, here's how we're going to think about a logarithm. The logarithm in a base of b, so b is going to be a number, every logarithm has a base, of the number a is going to be answer c if and only if, that is, that statement there is equivalent to this statement here, b to the c power gives a. Now let's stop and reflect on this for a second. There's 3 numbers on each side of this equivalence here. B is the base. Now whatever is the base in the logarithm statement is also the base in the exponential statement, so that's pretty nice. A is the number that goes into the logarithm, and C is the number that comes out. In the exponential statement, C is the number that goes into the exponential statement, and A is the number that comes out. Now what does that remind you of? A goes in, C comes out, C goes in, A comes out. That almost sounds like an inverse function kind of a thing, doesn't it? And in fact, that is the case. The logarithmic functions are just the inverses of the exponential functions with the same base. We'll talk about that more in a minute. Let's go ahead and compute some logarithms. So here I want to just find the logarithm in the base 10 of 100. Now it's fairly difficult to think about logarithm statements. It seems to be much easier to think about exponential statements. So this log base 10 of 100 equals, I guess we could call that x, is equivalent to saying 10 to the x power gets you 100. That is, in the logarithm statement, 100 goes in, x comes out. So in the exponential statement, x goes in, 100 comes out. But you see how much nicer it is to think about that one. Well, we can just guess the answer to that is 2. So log base 10 of 100 is going to be the number 2. Let's see if we can find logarithm base 2 of 8. Now we're thinking, what exponent should I put on 2 to get 8 for an answer? That is, what exponent should I put on 2 to get 8 for an answer? And in fact, that's a good way to think about logarithms. The logarithm is whatever exponent you put on the base to get that number for an answer. And again, this one is nice. It looks like a 3. Now, I know you're thinking, well, not everything's going to be quite so nice. I mean, what if we were trying to find log base 2 of 7? And you're right, that one would be not quite so nice. But for right now, we're going to limit our attention to those which are nice. I said for now. Let's find logarithm base 7 of 49. And so I'm thinking, what power would I put on 7 to get 49 for an answer? And of course that's a 2, because 7 squared is 49. I guess one more of these and then we'll go on. Logarithm base 8 of 4. Uh-oh. It looks like things have turned nasty already, haven't they? So now I'm thinking 8 to what power would give me a 4? 8 to what power would give me a 4? Well, it's not a 1/3 because the cube root of 8 is just 2, so this looks like a toughie. I don't think I can change that base 8 into a base 4, and I don't think I can change that base 4 into a base 8, not nicely. I think what I'm going to do is change both of them into base 2. So 8 is 2 cubed, and 4 is 2 squared. Now we remember from our properties of exponents that when you have a power raised to a power, you multiply. So here I've got 2 to the 3x power there is 2 to the second power. The only way this can be true, it must be that 3x has to have the same value as 2. 3x equals 2, and then we get that x is 2/3. Let's just check that. 8 to the 2/3, that would be the cube root of 8, which is 2, and then square it, and then you get 4. So, yeah. Log base 8 of 4 is 2/3. Okay. Now, log base b of x is the inverse. And remember, when I say inverse, I don't mean a reciprocal and I don't mean an opposite. I mean a functional inverse. Log base b of x is the inverse of b to the x power. Okay. Thus, if you take log base b of b to the x, the result of that should be the identity, just plain x. Now let's think about this one directly. See, the logarithm, what exponent do you have to put on b in order to render b to the x power? Why, of course that's x, right? B to the x is going to be b to the x, so that's almost an obviosity there. And also because log base b and b to the x are inverses, we have that b raised to the log base b of x, that's again going to be x. This one, provided x is greater than 0. You can't put negative numbers into logarithms if you want to stay in the set of real numbers, which we want to do. Okay, so those statements are true. Also, because log base b is the inverse of b to the x, I think I can nicely recover the graph of a logarithm. There's b to the x for b greater than 1. You can talk about logarithms which have a base less than 1, but nobody ever wants to. If you remember, the graph of a logarithm, or of an inverse, is the reflection through the line y equals x. And so if I reflect that, I guess I'll get, right here would be the graph of log base b of x, also for b greater than 1. Let's check that on the calculator and see if the calculator agrees with what we've come up with there. Okay, so I'm going to go to the y equals. It seems to be clear there. Okay. I'm going to choose b to be 3. Now I'm going to choose b to be 10. So there I'm going to put 10 to the x power. Sketch the graph. I've got some kind of a, okay, try zoom number 6. Okay, so there's b to the x. Now let me go to that draw. So there I want yellow button, draw. And I think it was number 8, but let me go check. Yeah, number 8 is to draw an inverse. I got to tell it y1, y bars, function. There it is. Enter. Okay, so those two graphs appear to be mirror images through the line y equals x. y equals, let's try this, and y2, I'm going to push log x. Now, just log, I'm going to make that darker. Okay. There's two logarithm buttons on your calculator. log with no base written is base 10. ln with no base written is base e. Now, and you notice that the calculator is arranged so that the inverse functions are together there on the same button. Pretty nice. Okay, so now notice that I turned this to a darker thing. Let's go ahead and graph those. Yeah, and so we see that the graph of log base 10 indeed does turn out to be the inverse of 10 to the x power there. That was a kind of a nice check. Okay, let's get this all together a little bit nicer. Graph y equals log base b of x be greater than 1. What we've discovered is that that graph comes through this way. It's going to have an x-intercept of 1. Asymptote here of the y-axis. Domain 0 to infinity. That makes sense because the range of 10 to the x was 0 to infinity, and when you do the inverse, you know the x and the y switch places. The range for the logarithm function is going to be the whole set of real numbers, which was the domain of the exponential function. So there's a graph that, you know, I would have my calculus students, I certainly hope they have that kind of a graph committed to memory. I would hate to think that I had an AP calculus student who didn't know what the graph of a logarithm function looked like before they ever walked into the door of my classroom. And if I did have students who came into the in through the door of my AP calculus class without knowing the graph of a logarithm, then I'd have to go speak to the pre-calculus teacher about that. But in my school system, I'm also the pre-calculus teacher, so I'd have to speak to myself about that. Let's practice some with just plain logarithms, and then we'll go and see what on earth this stuff is about, because right now, you know, everybody's wondering, wonder what the point is for these logarithm things. So we're going to get to see what the point is. Okay. First, I want to find some things. I'm going to find log base 4 of a half. Oh, so now we're thinking 4 to what power would give a half? Well, let's see. I don't know if we can guess that pretty nice. If I took the square root of 4, it would be 2. Aha! I think I can guess this one. If I took the square root of 4, it would be 2, so that would make x a half. But I want this to wind up being the reciprocal of 2, and so I guess x there would be negative 1/2. So the answers to logarithms can be negative. It's just that the inputs to logarithms can't be negatives. Okay, let's do some simplifying. Simplify 5 to the log base 5 of 3. Now, if you start doing this the hard way, then you're going to have a hard time doing it. If you do it the easy way, you'll have an easy way of doing it. See, if you look at the wrong part of this, you might think, well, first I have to figure out what is the log base 5 of 3. Well, that's not a friendly calculation. But if you look at the other part of it, what we have here is 5 to a power coupled with log base 5. And we know that the relationship of those two functions is those two are inverses. So whatever is under my thumb, that's what the result is going to be, because 5 to a power and log base 5 cancel each other out, and they're inverses. And so I guess the answer would be 3. That was pretty nice. But at first it looked a little intimidating. Simplify. Log 100 to the x. Now this just says log, and if you remember, that means base 10. So I wish this 100 was a 10. See, if that 100 was a 10, then the answer would be just x. So I'm going to go ahead and make that a 10, but I'll have to make it a 10 squared to the x. So then that becomes log of 10 to the 2x. And of course, that's when we can figure it out nicely. Final answer winds up being 2x. That's pretty friendly stuff. Okay, bearing a special mention is the logarithm base e. ln of x is log base e of x. So the usual convention, and I haven't seen exceptions to this, the convention is log means base 10, ln means base e. I believe one reason for that is back in the olden days, before there were fonts on computers, there were things called typesetting. And when you were printing a book, if you had to print that subscript all the time, it takes a lot longer to typeset, because the typesetting thing, it was a more complicated procedure to put subscripts and stuff in there. And so if you just make an agreement that log means base 10 and ln means base e, then it's a lot quicker to print your books. Okay, so ln of x, and that's called the natural logarithm. ln x is the natural log. Base 10 is called a common logarithm. So ln x is the inverse of e to the x power. That is, ln e to the x is x, and e to the ln of x, that's going to be x. So we'll do one more simplification here. I want to simplify ln e to the 7th power. And the ln of e to the 7th power would turn out to be just plain 7. And so, voila, finished with 3H. Almost finished with session 3. A couple more sections. You can now enjoy those problems that Carmen has selected for you in the problem set. 3H, not ready for a quiz yet. I. Logarithmic functions. Let me show you some properties of logarithms. Okay. Properties of logarithms. Logarithm base b of u times v is equal to log base b of u plus the log base b of v. Now let's stop and reflect upon this a little bit. On the left side of this equation, there's an operation multiply. On the right side of this equation, there's an operation add. So what does this equation do? It almost seems as though this equation changes the operation multiply into the operation add. Now that would be rather interesting. It turns out that logarithms were discovered. Now there's depending on your philosophy, you say either logarithms were invented or logarithms were discovered. Everybody answers that for themselves, but I believe logarithms were discovered, and they were discovered not by a mathematician, but by an astronomer. So originally, logarithms were astronomy. Mathematicians saw the neatness of certain things that logarithms do, so we went ahead and stole it. Everybody today thinks that logarithms are math, but originally logarithms were in astronomy, not math. We stole it. The astronomer's name was John Napier. He was a French astronomer. Now, one of the biggest things that astronomers have to do is they have to find distances between stars. And of course, these are really big numbers. Let's see, what's the closest star to Earth? The answer to that is the sun. Okay. The sun is a star. But if you ever take astronomy, you got to remember that, because that's the trick question on the first test. They ask you, what's the closest star to Earth? And everybody says Alpha Centauri and things like that. But it's the sun. The sun is 93 million miles away. It takes light about 8.5 minutes to get here from the sun. Now, light, travels really fast, but 93 million miles, that's quite a distance. So if the sun ever blows up, you've got 8.5 minutes left. And after that, things get mighty cold. So use those 8.5 minutes wisely. Just go ahead and do some logarithms or something like that, right? Of course, we won't know that the sun blew up for 8.5 minutes, because we'll still be looking at it. Now, the second closest star to Earth, that's Alpha Centauri. It's 4.5 light years away. That means it takes light 4.5 years to get here. If Alpha Centauri blows up, we won't even know it for 4.5 years. We'll still be watching it. So in fact, when you go out at night and look into the heavens, probably a lot of those stars blew up a long time ago, but we're still looking at them because it takes light so long to get here. Okay, now if you were John Napier back in the days of yesteryear, this was about 1600, see, you're pretty frustrated because you're trying to calculate distances in between stars, and 4.5 light years, that's a really big number of miles if you were measuring that in miles. So Napier was kind of frustrated. He didn't have a TI-83 to do all that arithmetic for him, and he was having to do calculations with really big numbers. So he thought up these things called logarithms, if we can come back to the sheet now. Okay. Let us suppose that u and v were a pair of really big numbers, and you had a choice of multiplying two really big numbers or doing an addition problem. If you're a clear thinker, you're going to choose to do an addition problem instead of multiplying two really big numbers. Okay. So Napier discovered these logarithms in order to facilitate calculations. Now today, as a calculation kind of a thing, logarithms are rather obsolete because, we've got these TI-83s that can not just do calculations faster, they can do it a lot more accurately than you can with these logarithms. So in that sense, it's kind of obsolete. However, when you get into calculus, you discover, let's just take product rule, for example, for derivatives. The product rule for doing derivatives of functions is considerably more complicated than the addition rule for doing these derivative things. So if you can change a multiplication into an addition in calculus, you've done yourself a good service there. Logarithms are not obsolete. Like I say, the mathematicians saw the goodness there, and we stole them. So if logarithms change multiplication into addition, by gosh, I bet they would change division into subtraction, and surely they do. Log base b of u divided by v is log base b of u minus log base b of v. And finally, logarithms change exponentiation into multiplication. So the log base b of u to the v power is v multiplied by the log base b of u. Now there are some other properties, but these are the main three. If you know those three, you can go a long distance in logarithms knowing those three. Let's go ahead and prove that the log base b of u times v is log base b of u plus log base b of v. I guess the general question of how much time in your class do you spend proving theorems and deriving formulas and that kind of stuff, that of course is up to you. At least I've never had a principal to come to me at the end of the day and say, Dave, did you prove property number 1 of logarithms today? Because, I mean, actually I've never had a principal who even knew there was a property number 1 of logarithms. So, you know, nobody's going to come and check up on you on how much you're proving and deriving. I suppose for me, it depends on the class. Okay, I'm going to let x represent the log base b of u, and I'm going to let y represent the log base b of v. Now, if x is the log base b of u, then that means b to the x power would be u, and b to the y power would be v. So that's just the equivalence between a logarithmic and an exponential statement there. Now, I'm going to start with that log base b of u times v, and I'm going to go through a chain of equality until I finally get to the right side of this statement here. So that would equal the log base b. U is b to the x, and v is b to the y. So there I did a substitution. And we have log base b. Oh my goodness. B to the x times b to the y. From our properties of exponents, we could make that b to the x plus y. That's something we already knew about. And then, since here we have log base b and b to a power, those two are inverse functions, so I can turn that into just x plus y. And finally, x was log base b of u, and y is log base b of v. And so by doing that, I would think we've gotten the flavor of how you would go ahead and prove some logarithm statements, and so I won't subject you to proofs of 2 and 3. Given log 5, 0.699, log 15, 1.176, find log 3. Find log 3. Well, somehow I have to use these given facts here, that the log of 5 is 0.699 and the log of 15 is 1.176. I guess 3 is 15 over 5. So this would be the log of 15 over 5, which of course is log 15 minus log 5. So now we're saying, whew, at first it almost seemed as though we were going to have to divide 0.699 into 1.176, but you see, that wasn't Napier's idea. His idea was to try to avoid doing that kind of stuff. So I've got 1.176 minus 0.699. Now I'm going to go to the calculator to do that calculation. And so, okay, get that out of there. 1.176 subtract 0.699, and I get a 0.477. Now if I just push the log of 3, over here's a log button, I'm just going to push that log 3, Now we didn't get exactly the same answer there. Of course, the reason for that is the log of 5 isn't exactly 0.699. It's an irrational number, and it was just approximated to do that. Now, here's the dilemma. If I were creating some test questions, you say, I wouldn't want the students to just push log of 3 and get the first 3 decimal places there. And on the other hand, I wouldn't want them to have to do that 1.176 minus 0.699 by hand either, right? So that is a dilemma for me, because I want the students to be able to use the calculator to do some arithmetic. However, I don't want them to use the calculator to avoid having understood the ideas. And let me tell you what I would do. I would really do this. In fact, I have really done this, that if I was wanting to do a test here, what I would have to do, when I give the given log of 5, instead of making that 0.699, I'd have to do something like make it 0.583, you see. So I would have to give them a wrong value for the given information here, and that way they can use their calculator, and if they sneak in there and push that logarithm button, I'll know what they did. So that's generally how I make up a logarithm test, by giving incorrect information. Another way to do that is to just call it A. Log 5 of A and log of 15 is B, but somehow that makes students nervous to have letters instead of numbers. Alright, well that was pretty much fun. Now we're going to use those same given values, that log of 5 is 0.699 and log of 15 is 1.176. And here I want to find the log of 125. Well, somehow I have to write 125 using 5s and 15s. Well, it just happens that 125 is 5 to the 3rd power, yes? Yeah, so this would be the log 5 to the 3rd power. And that, of course, is 3 times the log of 5. And so that would become 3 times 0.699. And then do that on the calculator. 3 times 0.699. And that's a 2.097. 2.097. Log 1/5. Now there's several ways I can do this, so let me go ahead and do this 2 different ways. On the one hand, I can make this a log of 5 to the negative 1 power, and on the other hand I can make this the log of 1 minus log of 5, because it was a fraction, so it went to subtraction, and 1/5 is 5 to the negative 1 power. So this becomes minus the log of 5. Now here I'm going to have to figure out something about the log of 1. Well, I can do that with brain power. The base is 10. 10 to what power gets me a 1? 0. Oh, I also knew that because 1 is the x-intercept in the graph of those logarithm functions. So that's a 0 minus the log of 5. And so either way, we're going to wind up with minus 0.699. And that problem can nicely be done either way. Now, if you don't want to mess around quite so much with those numbers, expand ln of 3xy cubed. Here's another way you can test on those ideas. So expand that. Well, this is a multiplication, so it turns into addition. This is log of 3 plus log of x plus log of y cubed. And then I guess there's One more thing we could do there, make that log of 3 plus log of x plus 3 times the log of y. Yeah. Okay, so there's a good way to test students on the properties. Or you can do that backwards. Condense. Condense. Here it is. Log base 5 of 8 minus the log base 5 of 12. Now by condense we mean use properties of logarithms, but this is a subtraction, so it must have come from a fraction, log base 5 of 8/12. I guess we should be complete here and go ahead and reduce that. 8/12, my recollection is, reduces to 2/3. So log base 5 of 2/3. It's another condense. Log base 3 of 2 plus 1/2 the log base 3 of y. Now you might be thinking, well, what happens on one of these problems if we didn't have the same base? Well, then, of course, we're in trouble there. This is the log base 3 of 2 plus log base 3 of y to the 1/2 power. And then we can make that log base 3 of 2y to the 1/2. If the base is not 10, then you have to write the base number. If the base is e, then you can write just ln instead. So there's some nice manipulations with properties. There's one more theorem. This theorem tells us how to change the base. I have never seen a calculator that had base 7, for example. Calculators will have base 10 and will have base e if they have logarithms at all, and that's all they're ever going to have. So if you ever need to find log base 7 of 5, you're in deep trouble there if you only know how to use a calculator. This change of base theorem is the theorem that provides a means by which you can do that. And then, if your students learn it here, by the time they get to calculus and their professor gives them differentiate log base 7 of x, they'll know how to do it then. Change of base theorem says the logarithm in a base b, I'm going to call the number capital N, can be changed to logarithm base a of n divided by logarithm base a of b. Now the n and the b were there to begin with on the left side of that equation, and we might wonder, where on earth did that a come from? Well, it turns out that a can be any number that you wish that's allowable for a base of a calculator, or of a logarithm. Probably you're going to want to choose a to be either 10 or e, because those are the buttons on the calculator there, right? So probably that's what you're going to want to choose. Let's see. Or this statement here would be equivalent to saying log base b of n times the log base a of b is equal to the log base a of n. So to get from here to here, all I did is multiplied both sides of the equation by log base a of b. Now the reason that I changed this is that the second version is the one that's easy to prove, and the first version is the one that you want to use. Okay, so I'm going to prove the second version, and if I do that, I think you'll believe that the first version of that was correct. So I'm going to start with log base b of n multiplied by the log base A of B. Now, one property of logarithms says, let me cover this up, right? Whatever is right here is a coefficient on the logarithm, and property number 3 of logarithm says this coefficient, if you want to, you can take and make it an exponent on that b. So, like if there was a 2 under my finger, I could make this log base A of b squared. Well, this becomes log base A of b to the log base b of n. Okay. So now, what on earth are we going to do with that? Why goodness, what a piece of luck. Look over here, we've got a b and we've got a base b up there. So those two are inverse functions, they cancel each other out, and we wind up with log base A of n, which is what the right side was, and so that's proved. Very simple to prove, change of base theorem. I suppose that's another thing I consider when I'm deciding how much stuff I'm going to prove and how much stuff I'm not going to prove. If there's something that's real easy to prove, you might as well go ahead and do it. Find log base 7 of 5. Find the logarithm base 7 of the number 5. Well, by the change of base theorem, I could make that log of 5 over log of 7. So there I chose base 10. Or I could even do ln of 5 divided by ln of 7. Let's compare them and see if we get the same thing. I'm going to go to the calculator there. Let me see. Now, to compute the top one here, I go LOG button, 5, put a parenthesis, divided by, see, now, here we go to this generational thing again. People of my age are suspicious about whether this is going to give us the right answer or not. Log of 5 divided by log of 7. See, here's my dilemma. I'm wondering, is this going to take the whole logarithm of 5 and divide it by the whole logarithm of 7, or is it going to take 5 and divide it by the logarithm of 7? I believe this one is okay. But you see, I have no intuition about that answer. So I said I believe this one is okay, but if that one wasn't okay, how would I know it? So let me try this one again. Now I'm going to put a parenthesis, log 5 divided by parenthesis log 7. So if this answer turns out to be the same, let me just mention here that the calculator doesn't recognize ends of lines. So even though this parenthesis is hanging by itself down here, that's just the way it is. That's okay. Now when I push the enter button here, I hope I'm going to get the same answer. I believe I'm going to. Got my fingers crossed. Voila. So it is okay to not put the parentheses in there. You'll still get the right answer. Let's check it with the natural logarithm. I'll take the ln of 5 divided by ln of 7. And there we do get, this turned out to be exactly the same result. It wouldn't have surprised me too much if, this might have been a little bit different way out there on the right there, because all these logarithms are approximations. Okay. So there's the change of base theorem, and frankly, there isn't a whole lot to that. It's just the way you do the change of base theorem. So far, we haven't seen any real good use of any of this logarithm stuff, but we will. But the real truth is, the powerful applications of logarithms don't come until a couple of courses later, when you need these to simplify expressions, to do these derivatives and calculus and all that. That finishes section 3, part I. You can do those problems. I know you'll have great fun doing so. Not ready for a quiz yet? J log and exponential equations. Now here again, when we talk about exponential equations, we're not talking about equations that have an exponent. We're talking about equations for which the variable appears as a part of an exponent. So let's do some solve. Right? Next few problems are all just solve. 3 to the x equals 9. Now looking at that, we're thinking, oh boy, hope there's a lot of those on that quiz. Because this one you can guess, the answer is just plain 2. But now, see, suppose things were not quite so nice. That was problem number 1. Problem number 2 is 3 to the x is 10. Now, of course, if you had to choose, if the quiz said choose one of these two equations to solve, a normal person would choose equation number 1. But, probably it's not going to be like that. Probably number 2 is what you're really going to get. It's not likely that we can change that 10 into a base of 3. At least it's not easy to do so. Now there's two good thoughts. One good thought would be to take the log base 3 of both sides. So let me go ahead and do this problem two different ways. I'm going to take the log base 3 of both sides. Log base 3 of both sides. Now why did I do that? Well, because log base 3 is the inverse of 3 to the x power. So if I'm trying to get the x down in the baseline, I want to get rid of that 3. And the way you do that is to put a log base 3. So the left is really nice now. It's just x. But unfortunately now on the right, I've got to find the log base 3 of 10. Well, the good news is we've got that change of base theorem. So that's log of 10 divided by log of 3. I'll go to the calculator there, get that stuff out of there. Push the log of 10 divided by log of 3, 2.096 if we round off there. We round off to 3 decimal places. Now the other good way to do that is just take log base 10 of both sides. Or I could take ln of both sides. That would be fine. Now the disadvantage to this is that here we've got log base 10 of 3 to the x, so those don't just cancel out. However, I can use property number 3 of logarithms and bring that x in the front there. Log of 3. Now look at there. Log of 10. I'm not going to use a calculator to compute the log of 10 because I know that the base is 10 and 10 to the first power is 10, but I mean there would have been nothing wrong with using the calculator there. X is 1 divided by log of 3, and so I can put 1 divided by log 3, and not surprisingly still get the same answer. And if you'd like to check, go ahead and do the same thing with the ln, and you'll still get the same answer there. So it's nice to know that math is still perfect. We don't do a problem by two different valid techniques and get different answers. We don't want that to happen. Equation number 3, we're still solving. 5 to the x plus 2 has got to equal 8. Well, I think this time I'm going to use the ln. ln 5 to the x plus 2 is ln of 8. By the way, I don't know why I decided to use ln here. I'm just trying to show you different ways of doing things. So now I'm going to bring the x plus 2 to the front, make it a coefficient, times the log of 5 is log of 8. So I guess if we take a negative 2 and add log of 8 over log of 5, negative 2 add log of 8 divided by log of 5. So I get negative 0.708. Let's go ahead and check one of these anyhow. 5 to the negative 0.708 plus 2 equals 8. So I'm going to come over here to the calculator. I'm going to push 5 upper parenthesis negative 0.708 plus 2. Now when I push this button, if the world is perfect, I'm going to get the number 8. If the world is only beautiful but not quite perfect, I might get 7.992 or something like that. I honestly don't know if this is going to turn out to be exactly 8. I do know that I'm not going to be upset if this is only very close to 8, because we've done a lot of approximating. Push the go button and I'm not upset, right? That's really close to 8. I believe the answer is as good as it's going to get. Good as it's going to get. Still solving. Number 4. Log base 2 of x is equal to 4. Now I could resort to a change of base theorem or doing something like that, but my goodness, the equivalence between a log and exponential statement would seem to be pretty good here. This base to that power has to get me x, so x would be just 2 to the 4th, and so there x is 16. That's all there is to that. That one was pretty simple. Log base 3 x plus 2 is equal to 5. So this one I would do by saying x plus 2 now has to be 3 to the 5th power. So it's x plus 2 is 243. What I did there is sneaked over and computed 3 to the 5th. So x is 241. Well, these seem to be not bad to do. Still solving. Number 6. ln 4x plus 1 equals ln now, in order to make this equation come true, what I have to do is make this equation come true. Now I know none of you were thinking this, but I know most of your students are thinking, oh, it looks like we divided both sides by ln. Now we understand that that's not what happened there. We did not divide both sides by ln. We did logic. We thought that the only way that this side can equal that side is if 4x plus 1 is 2x plus 5, or we exponentiated both sides base e, and then we have e and ln together and they cancel out. But I mean, you know your students are still thinking, oh, divide by ln, that's pretty slick. And so x is 2. If I put a 2 in there, I get log of 9 on the left and the log of 9 on the right, and that would seem to be what we wanted to happen. Let's try this one. Number 7. ln of x plus ln x plus 3 is equal to 1. So you see that this one is very different from that one up there. We can't just take away the ln's now or something crazy like that. Fortunately, we know those properties. This is an addition of logarithms, so it must have been a logarithm of a product, x times x plus 3 equals 1. Okay, now how do we get this back? Well, it looks like x times x plus 3 would now be e to the first power, which is just plain e. I can multiply this out. X squared plus 3x and then minus e has got to be 0, and there we have a quadratic equation. Now, my goodness, am I going to be able to factor that one? Oh, not nicely. So I guess we might need that good old quadratic formula. See, the quadratic formula has that property that when you're first learning it, you get 100 problems working the quadratic formula. And then if you forget it, a few months down the road when you really need the quadratic formula, see, on this problem, there isn't anything I can do here without knowing that quadratic formula. Let me write the equation down again. X squared plus 3x minus e is equal to 0. Well, I guess I could complete the square, but oh goodness. So it's the opposite of b, so negative 3, add or subtract, square root, b squared is 9, minus 4 times a times c, which is negative e, all over 2 times a. So negative 3 plus or minus. I'll tell you what I'm going to do. I'm going to compute that discriminant as a decimal number. So I'm coming to the calculator here. Now I'm going to compute 9, subtract. Let me just make that an add. Add 4e. 4e. Enter button there. Now I want to take the square root. So square root, answer, enter, 4.458. 4.458 divided by 2. And then I just go ahead and compute that. Let's see. 4.458, subtract 3, enter, divided by 2. On the one hand, I get a 0.729. On the other hand, negative 3, subtract, I get a negative 3.729. Okay. Now, I wonder if they both work. The original equation was ln x plus ln x plus 3 has to be 1. Oh, we see we've got trouble here now, don't we? Because, look at here. That negative number, we're not going to be able to put that negative number in here. Even though we might be able to go through some manipulation and things might work out here, the original equation is not defined. And so once again, we get an extraneous root. So the solution is only that x is 0.729. Always watch out for the extraneous roots. In a previous section, we had done some word problems with exponential growth, and there were two problems that we skipped, and I said we would do those in a later section, and now is the appropriate time to look at those two. So let's look at two more word problems that we have to do here. Question 5 was, the half-life of a radioactive element is 6 years. How long will it take for 10 milligrams to decompose to 4 milligrams? And question 6 was, the population of Mathobia was 1,500,000 in 1980 and 1,750,000 in 1990. Estimate the population of Mathobia in 2000. Alright, so let's take on number 5. The half-life of a radioactive element is 6 years. Now let's talk about this half-life concept. What you can't do is take 2 times a half-life and get a life. It doesn't work like that. So let us suppose that this was a hunk of uranium or some kind of a radioactive element. If the half-life there is 6 years, what that means is that at the end of 6 years, half of what used to be there has decomposed. We can think of it as disappearing, but it actually just changes somehow. Now, in another 6 years, the other half isn't going to disappear. In another 6 years, half of what is there is going to decompose again. So in another 6 years, half of what was there is going to decompose again. Right? So that's how a half-life works. So theoretically, there's always some radioactivity left there. But, of course, at some point it gets so small that you can no longer measure it. But it's an exponential function with a base less than 1, and that's called exponential decay instead of exponential growth. So we know that if A is the amount of radioactivity, in this case, is A naught e to the R times T, that's the same equation we were using before. Half-life is 6 years. Now that means if T is 6, the amount is going to be 1/2 of what we started with. Yeah? At T is 6, the amount would be 1/2 what we started with. So I'm going to go ahead and do that substitution. 1/2 whatever we started with is the initial amount times e to the r times 6. So what I'm going to do now is solve this equation for r, and then we'll have the growth coefficient. We can divide both sides by a naught. Now, just in case you're wondering, well, what if a naught happened to be 0? You see, that's silly to think about because a naught is the size of the initial sample. So if a naught is 0, then we didn't have a problem to begin with. So now I've got that 1/2 is e to the 6 times r. The reason I wanted to save this is because I wanted to do some of these with a logarithm. We had done some before by graphing the exponential function and finding a point of intersection, but I wanted to show you some of these using a logarithm. So how do we solve this equation? We take the log of both sides. Log of 1/2 is 6r, and of course there we had ln and e together, so they canceled each other out. And so log of 1/2 divided by 6, that's going to be the r. Now we'll go ahead and compute that. I'm going to take the log of 1/2 and divide it by 6. And I'm not surprised that the r there turns out to be a negative number. Oh, let's make it negative 1155. Negative 0.1155. The reason I said I'm not surprised that the r turns out to be negative, see, that in fact makes the base less than 1 instead of... So now we know that the amount at any given time is going to be the initial amount times e to the negative 0.1155 t. Okay. Now the question is, how long will it take for 60 milligrams to decompose to 4 milligrams. So what I'm going to do is I'm trying to get 4 milligrams. I'm going to start with 10 milligrams, e to the negative 0.1155 t. And then all I have to do is solve this equation for t, and we'll have that time. You know, whoever made this problem up, they could have been a little bit nicer, and they could have said 5 milligrams, and then in that case the answer would have been 6. So I'm supposing here that the answer has got to be a little bit bigger than 6. If the answer doesn't turn out to be bigger than 6, we're in trouble. So I divide both sides by 10. 0.4 is e to the negative 0.1155 t. And we take the log of both sides. Log of 0.4 is negative 0.1155 t. Log 0.4 divided by negative 0.1155 is going to be t. Log 0.4 negative 0. Well, I come up with t being 7.933 years. A little bit bigger than 6, so we believe we got the correct answer there. It is my intuition is agreeing with the answer. Okay. The other word problem that we had skipped before, the population of Methodia was 1.5 million in 1980 and 1.75 million in 1990. Estimate the population of Methodia in 2000. So here's what we've got. 1980, we've got 1.5 million. 1990, got 1.75 million. And we're trying to find 2000. Now, it just occurred to me that, you know, beginning students at first would look at this and say, well, look at there, we grew 250,000, so if we grow another 250,000, we're going to get 2 million in the year 2000. That's because people tend to think linearly. If population growth was a linear kind of a thing, then the answer indeed would be 2 million in the year 2000. But we know that population growths are not linear. They're exponential. That's what we're looking for. If A is the amount of people, we know it's got to be A naught e to the r times t. So I'm going to take A naught to be that 1.5 million. So right there we're going to call t equals 0. And then this would be t equals 10. That's 10 years down the road. And this would be t equals 20. We could have done this by calling 1990 A naught, and then this would be t equals negative 10. But this seems like the logical way to do it, so I'll go ahead and do it that way. Alright, so I'm going to put in what I know. That's 1.5 e to the r times t. Now, what else do we know? When t is 10, the population is going to be 1.75. So 1.75, if you remember, these problems are just a matter of putting the right number in the right place. And so 1.75 over 1.5 is e to the 10r. Might as well divide that out. 1.75 divided by Okay, it's a 1.1666. Now I'm going to take the natural log of both sides. Of course, I'm using the natural log because the exponential is base e. So the natural log, 1.167, has got to be 10r log 1.167 divided by 10. It's got to be the r number, log 1.167. R is 0.015. 0.015. So the amount has to be the initial amount, 1.5 e to the 0.015 t. Now let's go back to the beginning here. We see what we're looking for is t is 20, and so I'm going to put a 20 in there. The amount at time 20 is 1.5 times e 0.015 times 20. Now if we can look at the calculator, you remember there was that thing you had to watch out for when you're computing this. 1.5, yellow button ln is e to the x, and it asks you what the exponent's going to be. 0.015 times button 20 2.025. $2.025 million. So if we can come back to the paper. Okay. We say again now, if this growth was linear, then it would have been exactly 2 million right here. So because this is exponential, we're going along that curve instead. And so the population is a little bit bigger than 2 million in the year 2000. I guess it's fairly important to be able to predict populations down the road because just look, for example, at building plants that produce electricity, right? You need to know how your area is going to grow years down the road because it takes a long time to build a power plant because they've got to get all sorts of permits and the construction itself takes a long time. So if you have inaccurate predictors, some people have to go without electricity, and lots of things like that. Well, that finishes 2J. That's not a good sports car. All right, so you can now work the problems in session 2J. One more section and you're ready for quiz 3. Did I say 2 again? I seem to be fixated on 2. 3J. The logistic curve. Okay. The logistic curve is something that I think is fairly new. At least a few years ago, I had never heard of a logistic curve. Then all of a sudden it started popping up in all the books there. The reason, I believe, for that is that the calculations involved in doing some of these problems is just too difficult to do without some electronic assistance. Okay. Logistic curve. Suppose we put some rabbits on an island which previously had no rabbits. Further suppose there are no rabbit predators on this island. which graph most likely describes the population of rabbits? So that by that I mean time goes this way and the number of bunnies goes up that way, right? So the x-axis is time, the y-axis is population. Well, here we have a population that's growing, but it looks like that population would grow in a linear kind of a sense. In B, we have a population that's decreasing. Now, with what I know about rabbits, if you put some rabbits on that island and there's no rabbit predators, the population is not going to decrease over time. So I think B is not a good choice. A would be better than B, but I don't think A is quite right. Now, C says the population is fluctuating up and down and up and down and up and down. And I don't think that's what's going to happen. D is a population which is increasing at an increasing rate. Now, when I say that this population is increasing at an increasing rate, I mean the growth rate over here is greater than the growth rate over there. By that I mean the slope of the tangent line here is less than the slope of the tangent line over there. Getting ready for some calculus thinking. Okay, A, B, C, D. Which do you believe would be the best? D. Yes? Now, up until a few years ago, D was the correct answer to this question. And it turns out that D, in fact, is the beginning of the correct answer to this question. But I think there's another possibility that, like I say, up until a few years ago, nobody ever talked about. Okay. I believe E might be the best describer of the population, better than D. Now you notice that in the beginning, this graph looks very similar to graph D, but you know that the bunny population is not going to continue growing exponentially like that, just like you know that world population on Earth is not going to continue growing exponentially like that. We talked once about the ability to sustain a population only grows linearly. So even though, you know, at first the population seems to be increasing very steeply, even world population at some point has got to level off there when you start getting close to the ability to be sustained. So I think choice E might be the best, and it's called a logistic curve. Logistic curve. It turns out that not only is a population of rabbits on an island described by a logistic curve, there are many, many things that are described by a logistic curve. For example, if we were talking about the percent of households in the United States that have a personal computer. Right? Now at first, you know, when personal computers first came out, very few households could afford or even had an interest in having a personal computer. So not only was that number slow, that growth was pretty slow, but once, you know, people started getting them and the price started coming down, then the interest in having a personal computer at home started growing, and then there was a tremendous growth. But you see, that tremendous growth is not going to continue forever, because at some point you're getting pretty close to 100% of the households having a personal computer. And so I believe the behavior here would be asymptotic, as a horizontal asymptote in here somewhere, and in fact that's got to be true. If we were talking about the percentage of households in the United States that have a personal computer, right, that's going to get, I'm pretty sure, approach 100% as a asymptotic kind of a behavior. It'll never get to be 100% because there's always going to be some people who have no interest in a personal computer. My dad's 83 years old. Does he have an interest in having a personal computer? No. He lives in a senior citizen place where they're trying to show all the people how to do email and stuff like that. And I wish he would, because he lives quite a far away there. So email would be very nice. We could communicate every day, but is he going to learn a computer? No. So never, if we look back at the graph here, never would the percentage of households having a personal computer really get to 100%, but it'll get pretty close to that as time goes on. Just many things are logistic. And so you wonder, why on earth haven't we heard about this logistic curve for a long time now? Well, I'm going to show you why. The function is very complicated. If n, I'll use n now for the number of rabbits, n of t would turn out to be, I'm going to call this c divided by 1 plus a times e to the negative rt. C called the carrying capacity What that means, that's the asymptote line. Okay? For the bunny rabbits, that number C would represent the most rabbits that could be sustained on that island. For the personal computer problem, that carrying capacity is that line y equals 100%. Okay? So that's the asymptotic line. C, A, just a constant, and R is going to be a growth rate in there somehow. Now let me talk a little bit about this carrying capacity thing. We'll notice that A times E to the negative RT is A divided by E to the RT power. Now we had talked about end behavior for polynomials, but look at this. As t gets big, r times t gets big, and e to a big power is going to be a big number. So as t gets bigger, a over e to the rt gets small. As t heads towards infinity, a over e to the rt gets small, heads toward 0, and so c over 1 plus a e to the negative rt is going to head toward c divided by 1 plus 0, since a over e to the rt gets small, and of course that's c. So that's why the numerator, the number in the numerator there, becomes the carrying capacity. As time goes on, the number gets closer and closer to that number c. Right? So there's the general function there. Don't worry, you do not have to commit that general function to memory. So those of you who are already saying, oh no, I'm not going to like this section, don't worry, you're going to like this section. Nice section. Let me do a problem. Instead of doing a problem that has only numbers, let's look at an implied problem. Okay, so here we have total sales of a new CD. It says, the Mathophonics have released a new CD, Rocking with Logarithms. I'm sure there would be a lot of interest in that. Although the sales were somewhat slow at first. Now, I can't imagine the sales of that being slow, but it says that although the sales were somewhat slow at first, gradually the CD audience realized there was rhythm in those rhythms, and soon the sales skyrocketed. The chart gives the total sales over several months. So T is going to be in months, and here we got sales in thousands. Okay, so I guess to begin with, we had 500 sales. At the end of the first month, we had 2,000 sales, and so forth. Right? We've got some data here. Now, it might have been that it made more sense that at time 0 we had 0 sales. Okay, that might make logical sense right here, but it turns out that when you do the logistic regression, it doesn't accept if you have a 0.00. So I had to finagle that number a little bit in there. It took me a while to figure that out, but the calculator won't accept 00 as an entry. So, you know, if you had a 00, what you would do is put in 0 and 0.1 or something like that. Won't change very much. So this is for over the first 7 months. Question A says, graph the sales function. B, estimate the total sales. Now, by the total sales, we mean, you know, if you go out there 17 years, you know, how many CDs are you eventually going to sell? When were the sales growing most rapidly? That's called the point of diminishing returns. We're going to talk about all that. All right, let's go to the calculator. So as I was saying, I believe that one of the reasons we never heard about this logistic curve before we got the technology to an advanced state is the calculations are just too ridiculous to try to do by hand. Okay, so I'm going to turn it on. It's already on. I'm going to push this button here called Statistics, a Stat button. Okay. First, I want to put some numbers in. To put numbers in, you go to Edit. So I'm going to push Enter for Edit. Now, there's already some numbers left over in there from better days. So if you remember how to get rid of those, you push up arrow, and then clear, and then down arrow. And when you do that, L2 has disappeared. Now I'm going to go right arrow. I'll push up arrow, clear, down arrow. That erases all those numbers. Oh, I could have done this in L3 and L4. You see, there are six stacks in here that you can put numbers in, but I don't know. I just always use 1 and 2. Seems most convenient that way. So I'm going to enter the data. In L1, I'm going to put the months. So 0, 1, 2, 3, 4, 5, 6, 7. Okay. So there's actually 8 entries there because we started with 0. Now I'm going to go to the right, and I'm going to put in there a 0.5, and a 2, and an 8, and a 33, and a 95, 258, 403, 496. Now, just looking at this chart, you know, one of the questions was, when are the sales growing most rapidly? It looks to me here we got from 95 to 258. That's pretty rapid. And from 258 to 403. So it looks like round about there somewhere is where the sales are growing most rapidly. But we're going to do this with the graph. Okay. Now I'm going to go back to Stat. Okay, so I'll push that Stat button. We've already got some stuff in the stacks. I'm going to go to the right, Calculate. Linear regression, we've done that before. Quadratic, cubic, quartic. Now those 5, 6, and 7, you would use those if ever your data appears to have that kind of a shape. Linear regression, and we talked before about that. 4 and 8, the only difference is, does the slope or the y-intercept appear first? I don't know why they would put... Now that's a logarithmic regression. So if you had some data that seemed to be in that kind of a shape, you would use that. And if you had data that seemed to be exponential, you would use that. Power regression, that's like x to the 7th power or something. Well, looky there, logistic regression. And then you can do a sinusoid too. Now, we're not going to do those in this course. You'll have to take the pre-calc course if you want to see anything with sine functions. All right, so we want to do a logistic regression. I'm going to push the enter button. I should have looked at the data first. Let me quit this. Doggone it. Okay, so let me do window here. Stat, edit. Now the x-axis has to go up as far as at least a number 7, and the y-axis has to go up to a 496. 496. I'm going to go here to window. X-min, we don't need negatives. I guess I'll put a 0 in there. 0 to 10 will be fine. Now, y-axis, I guess we can go from 0 to, I don't know, 500, 496. 500 should get that one okay. All right. Let me go to the stat plots. Plot number 1 is L1 and L2. It's turned off. I'm going to push the enter button. I'll push the enter again, turns that one on. And highlighted is still the isolated dots. We have L1 and L2. And we're going to do the box. Let me show you how to change those if you ever do want to. The L1s. I push down, down again. Now, L1 is highlighted. If I wanted to do a regression where the x-axis was in L3, this is what I would do. I noticed that down here above number 1 in yellow is L1 and above number 3 is L3. So if I just push yellow button number 3, see what that does is put that L3 in there. So you can't type the letter L and then the number 3. You have to use that special button. Now I got to change it back to L1. Okay. That's set up ready to go. The window is set up ready to go. That stat plot is turned on, I believe. I'm going to clear, push the graph button. And what we see is, it looks like points that are a nice logistic curve, not surprisingly. Now I notice, remember that with a calculator it's most often most efficient to take a guess and see that things are coming okay. This one seems to have disappeared and that one seems to have disappeared, so I'm going to change that window a little bit. The y coordinates, I'm going to put in there a -10 again, and instead of 500 I'm going to make it 550. Right. Now let me push the graph and see if it looks a little better. I guess it's a little better. I can see things a little bit nicer there. I think 600 might have been nicer. 600. Okay, that's looking pretty good. Now you do want to come up with a window that gives you that nice characteristic S. All logistic curves have that nice characteristic S. Okay. Now I'm going to go to Stat. I'm going to go right to Calculate. B is Logistic Curve. Push the Enter. I only have stuff in L1 and L2, so I don't have to tell it L1 and L2, but I would like it to find this equation and put that equation in Y1. So I'm going to go to Vars, right to Y bars. We want function, and there's Y1. Push Enter. Okay. Now when I push the Go button, the calculator is going to start working. We've had, even if you had never seen a TI-83 before you started this course, we've had a good bit of experience with this calculator now, so by now you know it's a pretty fast thing. It's certainly a lot faster than we can do with pencil and paper. Because I don't know how many calculations a second this calculator does, and in fact I know almost nothing about what goes on inside that calculator, but you know, that's just like driving a car. You don't have to be able to know what goes on in the engine in order to effectively drive your car, and same way here. But what you do know is that if it takes a while for this calculator to do something, the something that it was doing was a very complicated process. So, on your mark, get set, go. Now, this thing up here I call the worm. As long as that worm is squirming there, the calculator is thinking. So I know that my calculator is not broken, it's just thinking. And if it has to think for a long time, that means it was doing something very complicated. You see here the general form for the logistic curve. C over 1 plus a e to the negative bx is the way they wrote it down, and they found those numbers a, b, and c for us. Now the reason that I've put that y1 after the regression thing is that this will now go ahead and type that into y1. Let's go to y1. See, it put all that in there for us. We didn't have to type all that out. And if I now go to the graph, if we can come back to the calculator. All right. Well, looky there. So there we found a function whose graph goes pretty close to those points right there. Now remember, it took this calculator a long time to do those calculations, and that's why we had never heard of the logistic curve until just very recently, because we didn't have the technology to effectively deal with that logistic curve. Alright, let's come back to the questions now and see what we're supposed to be doing. The question, A, graph the sales function. We've got that done. B, estimate the total sales. Well, let me go ahead and copy this function. Or let me round some things off here. It looks like that function was something like, I'm going to go to y equals 531.632. I just make that 532 over 1 plus 869 e to the negative 1.3. Okay, so A asks us to graph the function, and it of course looks something like that. B, estimate the total sales. Now that is that carrying capacity. So the total sales here, 532. CDs. So it looks like the Mathophonics didn't do all that great with their CD. They're going to sell, you know, probably a little over 500 of them there. Well, when were the sales growing most rapidly? Point of diminishing returns. Now, that's this point right here. That's called the point of diminishing returns. You see here that on this part, the number is increasing at an increasing rate, but once we get to that point of diminishing returns, it would be increasing at a decreasing rate. It turns out that this point of inflection here always happens at about halfway to your carrying capacity. So C, when were sales growing most rapidly? When sales were, let's say around about 270 or so, something like that. And then I could even come over to the calculator here. Okay, I'm going to go to the graph and do the trace button. Ah, now you see where the spider is jumping there. It's on that one. Let me see if I can get it to go to the other curve. I'm going to push the up button. Aha. So I want around about 270. There's 287, 269. I'd say, oh, around about month 5. Around about month 5 is when the sales were growing most rapidly, and that is that point of diminishing returns. And so, there it comes. Oh, here it comes. Well, there it is. Not only have you finished section 3, this part, you have finished all of section 3. So it's now time to enjoy another one of Carmen's quizzes. That'll give you 3 down, 1 to go.